Good afternoon, and welcome to SIGGRAPH 2013. So my name is Dave Shreiner, and this is my colleague Ed Angel. And welcome to the Introduction to OpenGL course.
Yeah, right. Morning, afternoon. Hi, I'm Ed Angel, and as Dave pointed out, we've been doing this course for quite a while, and it's been changing. I mean, it's been changing because OpenGL has changed dramatically, but it's also changed in terms of the way we present the course here, because what we've tried to do, especially there, and I really think we got it right now, is to get really focused on an introduction to OpenGL programming, not to try and put in a lot of the advanced topics, because there's always some people in here who want to know about the latest things. This is really to help you get started doing your first applications with a modern OpenGL. Now, let me start by giving a little bit of an outline of what we're going to do. Dave is going to come up here in a couple of minutes and talk about how the OpenGL pipeline and how it's evolved over time, and that'll get to sort of where we are now in OpenGL and the various versions of OpenGL that are available, and then it'll help you, I think, place what we're going to do today in the realm of the totality of what's available in OpenGL. Then I'm going to come back and talk about an application. We're going to do a very straightforward application, a rotating cube, but the importance of it is that everything that's in that application is pretty much everything you need to do more complex applications. It'll eventually have some interaction, it'll have colors, it'll have modeling of objects, and so once I think you've grasped that, you'll have a pretty good idea of how OpenGL works and how you can get started with your first applications. Now, what we'll see in this is that everything we do in modern OpenGL depends on shaders. And so Dave will come back after I'm finished and start a discussion of vertex and fragment shaders, which are the two principal kinds that are required now in every OpenGL program, and he'll go through that. Then I'll come back and we'll talk about, well, what can you really do with these shaders? And I'll give some examples of what you can do with both vertex and fragment shaders. And the final part, which is not on this slide, is that we'll talk a little bit about texture mapping and how you can add that to your graphics. Okay, so what is OpenGL? And I think it's important here to understand that OpenGL is concerned just with rendering. It's concerned only with the graphics part of what you do in an application. It's not concerned in itself with the input. It's not concerned with the windowing system. It's only concerned with how do you take descriptions of geometric objects and their attributes like their colors and their texture maps, and how do you display that information on some sort of an output device. Everything else is not itself part of OpenGL, but of course, as we go through this, you'll see that you have to have those interactions somewhere in here. The other part of this is that because OpenGL in itself is not concerned with windowing and input, OpenGL is therefore platform independent, it's operating system independent, which means that you will be able to develop portable applications. But on the other hand, those applications in classic OpenGL, where you write a C or C++ program, will have to be recompiled on the local system, but the source code, at least for that part, should remain unchanged. Now, as I said, we're going to concentrate only on the latest versions of OpenGL, and the latest versions abandoned, and starting with version 3.0, 3.1, abandoned the old fixed function pipeline where you constructed programs with a lot of low-level functions like GL vertex. You said, here's a vertex, here's another vertex, here's a color, here's another color. All of that is gone now. And the reason that that's gone is because the power of modern GPUs has made it possible to do things way beyond what we had envisioned when OpenGL was created. And having all of those old functions in there really impeded not only the development of drivers for and GPUs, but also impeded, I think, the application developers because they were writing things in an old way which really wasn't making use of the full capabilities of modern GPUs. So this is going to be a totally shader-based discussion, no discussion of any of the old fixed function functions, but because you want to do those things. For example, you want to have lighting and you want to have colors and you want to have vertices to define your objects. We are going to talk about those things, but we're going to talk about how you provide those things in your own applications. And so the basic rule is that every application must provide at least a vertex shader and at least a fragment shader. And that's what we're going to see today. Okay, so I'm going to turn it over to Dave. Dave's going to talk about for a short while about how OpenGL has evolved and up through the latest stages of variants of OpenGL.
So I'm going to talk a little bit about the evolution of the OpenGL pipeline. For over 20 years. It celebrated its 20th anniversary last year. And I wrote the first commercial course to go along with it, so I tracked the evolution through a long time. As soon as we get the slides up, I'll talk a little bit about the evolution. When OpenGL was first developed, it was set up to really match the way the hardware was set up in the day. And a long time ago, I'm not sure, my first computer was a Commodore VIC-20, so I was familiar with peek and poke, right? You wrote things into memory. And that's actually how the original OpenGL was kind of structured. You'd send small bits of data down to the pipeline. As it evolved over time, it tried to match and include all the features of modern hardware. In the intervening 20 years, computer architectures have changed massively, and you'll see those changes reflected in the OpenGL API. Fantastic. So, once again, my apologies for the slide mess up. Microsoft stock dropped 20% the other day, but anyways. Okay, so the original pipeline was called fixed function. And just to go through the part of this, imagine OpenGL is a huge piece of machinery with lots of dials and knobs in the front. And you could kind of control those, flip switches to modify how it operated. But fundamentally, you couldn't change how the internals were actually accomplished. But it was a great API for solving the problem of doing the kind of graphics you did a while ago, back in the day. We'll get this squared away. Fantastic. I was glad all this is getting recorded. So the original pipeline matched a lot of what you find in classic graphics pipelines. And you'll see this kind of diagram and this pipeline evolving through the OpenGL side of things. It's just that we've modified the operation of it. So OpenGL is actually pretty simple. It knows how to draw points, lines, and triangles, full stop. And it knows how to deal a little bit with pixel data. We'll talk more about how you take an image and apply it to what we call geometric primitives. And that's our points, lines, and triangles. And the data would flow from the left-hand side of the screen through this pipeline off to the right, and of course, you generate a TPy. Sadly, OpenGL never adopted one of those as a fundamental primitive because it would have made our lives all much easier. But nonetheless, you're capable of rendering all sorts of things that go through there. Now, the boxes in blue are things that are exposed to you through the API, and you'll see this theme continue as I describe more parts of the pipeline. The red-colored box there is built into the hardware, and that's one piece you'll find is constant through the entire thing. OpenGL's never changed its rasterization mechanisms, right? And the rasterizer is just the bit that figures out which dots on the screen need to be illuminated. Are you plugged in? Right. Fantastic. So, in around 1994, so that was 1991, OpenGL 2.0 officially added a feature called programmability. And this allowed you to create something called a shader. A shader is another kind of program. It's written in a special language called GLSL. And we'll talk considerably about this in this course because it's the fundamental element of making all modern OpenGL go. Back in the day, they had slightly different versions of the shading language, but nonetheless, it allowed you to basically replace, is this the laser pointer? These stages here, the vertex, transform, and lighting, and the fragment and coloring, with some additional functionality. Now, 2.0 was a nice flexible API because it allowed you to use the old school way of doing things, but also began to show the features of what was coming down the pipeline. Now, that fixed function was still there, but as we've moved forward to OpenGL 3.0, which was released in 2009, it basically recognized the fact that, you know, in 17 years, an awful lot of things had changed in the architecture of computers, the way people were doing computer graphics, and in fact, the state of the art that was available in computer graphics. So OpenGL 3.0 introduced a very interesting change that was fully implemented in 3.1. 3.0 was the first API to actually go, hey, we're going to remove some stuff, or the first version to remove some stuff from the API. And in particular, what they did was they removed the fixed function pipeline. This was done for reasons of performance. You used to feed the pipeline with very small bits of data. So you'd say, here's a vertex, here's a vertex, here's a vertex. Modern hardware doesn't like to be fed tiny bits of hardware, or tiny bits of information. It likes nice large chunks. And so the modern GL was set up to more match the hardware that was there. Additionally, programmability became to the front of the party. All modern hardware had been programmable for quite a long time, and the fixed function was just a piece on top of it. So it turns out that at the time, the thinking was, well, okay, you know, we really want to get rid of this old stuff. We want to move forward, and so they developed a couple of concepts called contexts that had been a while, but they broke them into two categories. One's a full context, which had all the features of OpenGL. Another one was forward compatible to tell you, hey, these are the things that we're going to remove in the future, just to help you work with this. Now, Ed and I have been working with a lot of folks on this. To be truthful, I haven't heard of too many people leveraging the forward compatible context to see how it goes. Normally, this is for people doing really high-end cutting things on the most verdant hardware. Turns out, well, okay, it was a good idea, but we haven't seen the uptake that we were kind of hoping for. Now, OpenGL 3.1 is the one that officially removed all the old features and really brought the shading concept to the forefront. And in that case, you remember there were some couple of boxes that said vertex transform and lighting was one of them, and fragment shading and texture mapping was the other box. They've now been labeled by these kind of blobs that just say vertex shader and fragment shader. This marked a real large change in the way that you programmed OpenGL, because now you had to understand the fundamental concepts that actually are needed to do computer graphics. You have to understand matrix transforms. You have to understand projection. You have to understand what a viewport is. You have to have these concepts called texture mapping. Now, I just spouted a whole bunch of words. If none of those make sense, rest assured, Ed and I will explain all of them and tell you how to integrate it into this new form. The reason this was done, of course, is once again for performance. Modern hardware is insanely fast. You know, we're talking about drawing close to a giga triangles a second nowadays on desktop hardware, right? $300 and you're able to draw, well, many, many worlds with astounding realism. And you don't want the API to get in the way of all these kind of things. So that's why we've kind of modified everything. Here's one important point, and Ed will touch on this later. All the data that's now sent into OpenGL with 3.1 and forward is all GPU resident. So let's see, hopefully most people in here are C programmers, C++. Everyone's heard of memcopy? Yeah, excellent. Basically, OpenGL now has kind of something like a memcopy function. It's called GL buffer data, and Ed will talk more about that, which takes and copies data from the CPU down into the GPU. Turns out that the buses and GPUs far exceed the system capacity that's available in your PC or your notebook. And to get all that performance I just mentioned, you have to give the GPU the data and let it take control of it. This is actually a pretty good thing. It allows the driver to free-format data if it's necessary, or any of the other things to give you optimal performance. Now, this is what the pipeline looked like. You notice there's nothing fundamentally different since the original part of OpenGL except the vertex and fragment shaders. The stages are still the same, so we still just have the same fundamental concepts. Now, don't let me undercut the power of any of the shading models, because being able to program vertex shader allowed many, many great techniques to come on board. We've got motion blur that's in there, skinning was available, a lot of things that previously were very difficult to do. Now, as we move forward, OpenGL 3.2 was the next large advancement, and then that happened in 2009 as well. And that added a new shading stage called geometry shading. Unfortunately, we won't talk much more about that in this course. It's a bit of an advanced thing. But the fundamental idea is, right, OpenGL knows how to draw, as you've learned just moments ago, points, lines, and triangles. A geometry shader will take one of those, it'll take a point, and you can do pretty much anything you want to it. You can convert it into one triangle, into 100 triangles. There's just a limitation of how much data you can generate out of this. But this made for really interesting techniques for doing things like geometry compression or displacement mapping. Now, those words may make sense to you, and great if they do, and if they don't, now you have a reading assignment. Go out and enjoy some of the great literature that SIGGRAPH's put out over the years to understand how these great techniques are doing. It used to be this required, you know, massive computers or lots of clusters to do that. Now, actually, you can do it in your cell phone, which is pretty exciting. So, geometry shading, that was the next advancement in the pipeline. But there's also another part that came through. You remember I mentioned 3.1 chopped out all these features. Well, it turned out people actually were still using those features. There's some software that has been around predating OpenGL, and OpenGL was added onto it and really has continued to use the base features of it. So The OpenGL ARB, which is the body that controls the evolution of OpenGL, said, hey, let's find a convenient way to put all that back in and allow people to get access to all the new features, but if they've got legacy code or want to use the older style, we put all that back, and they replaced it with something called the compatibility profile. It originally started as an extension, and we won't talk much about extensions in this, but that's the way OpenGL evolves. A vendor or somebody will have an idea of like, this functionality should be part of OpenGL, and they'll create a little bolt-on piece to the API. It's not part of the core, it's some functions that you have to jump through some hoops to get it. This was the original way that was exposed, and that was a nightmare. So what they've done now is you can create one of these contexts to be either core or compatible. Core gives you the really trimmed down fast version. Compatible gives you just as fast version. It's the same code, but a lot more API to give data presentations to different ways. Now, once again, if you're going to feed the pipeline little piecemeal bits of data, you get what you pay for. Once again, forward compatibility is there, but we kind of touched on that before. Now, the last part is OpenGL 4.1, and that's added some even more advanced features called tessellation. Tessellation is a way to deal with splines and surfaces inside of the OpenGL pipeline. It turns out, I mentioned this before, but I haven't called it out exactly, the largest bottleneck in doing graphics nowadays is actually transferring data from the main CPU down into the GPU. Things like geometry shaders and tessellation shaders allow you to create geometry on the GPU, so we can cut out the slow middleman. And that's where you're really seeing these explosive growths and being able to generate a lot of triangles. Once again, the tessellation feature is a little beyond the scope of the course, but it's new features that are available on, well, actually it's now been out for a couple of years, and it's being incorporated into the games. It allows some really amazing techniques that have only been available through things like ray tracing, like displacement mapping, and adaptive tessellation. It used to take a lot of work to do that. Now you write just another shader. One thing that's really important about this is, where did the laser pointer go? You'll notice the shading element coming in here. We had originally had vertex shading and we had fragment shading. Those were the two stages. Then we added geometry shading, and now we added even more shading. So what's important about this is it's the same shading language. It's not like C or C++, but it's a very close derivative of it. It's called GLSL, and we'll talk much more about it as we go through the course. But you can see what's happened. Well, we write some data, and then we just process it through all these graphics techniques that we author ourselves through shaders. That's going to be a real large part of this course, is discussing how you construct these shaders and the processing that needs to occur with them. So there are a couple derivatives of OpenGL as well that are out there and actually gaining a lot of traction in the marketplace. The nice thing about OpenGL is that if you learn one of these, you can transfer skills back and forth between the two very similarly. The function names are very similar, the concepts are almost identical, and they're all shader-based. Now, there are a few limitations, and I'll talk about those just quickly. OpenGL ES stands for Embedded Subsystem, and that's what you find in most of your modern mobile phones. So if you have a smartphone with a color screen on it, odds are it runs OpenGL ES 2.0. It turns out there's even a more modern version called OpenGL ES 3.0. It's just that the hardware cycle on phones doesn't advance the same rate as desktop, so it takes a little longer to get drivers out to you and the hardware capable of doing that. You'll see that really in all the cell phones probably coming out in the next year. This is very much like OpenGL 3.1. It's a very trimmed down version of it. You have your vertex shader, you have your fragment shader, you have your data flowing through the pipeline. It matches that. It's just set up for working in an embedded environment. So there's some data type representation issues and a couple of things about precision. Their details, for the most part, you can write your code and be able to take it back and forth between ES and regular GL with no problems. Another one, and personally, Ed and I are extraordinarily excited about this, is one called WebGL. And this is 3D graphics, interactive 3D graphics inside of web browsers. WebGL exposes an OpenGL ES 2.0-like API. It's just wrapped up in JavaScript, which is this kind of wacky version of something that looks kind of like C if you squint and glance from the side. Once you get your head around the fact that it is really a very powerful language, WebGL becomes incredibly powerful. Basically, now instead of having to worry about windowing and some of the things that we'll talk about using this library called Glut in just a moment, WebGL says create to make a window is 2 lines of HTML. And then you have a little bit of JavaScript that goes, hey, make me a context, and then you're off and running. The simplicity of the system and how it's integrated into the web is really, really revolutionary. In fact, Ed has a textbook that he occasionally asks me to help him out with, and we're converting that over to work with WebGL. You think this is really fundamental stuff, and it makes the process of learning this really, really great. There are a tremendous amount of websites that are out there to show the kind of power that you can do. And the cool thing is, so much of the agony of working with C and C++, handling extra libraries and things, just out the window. So if you're in for enhancing your resume and having a good bit of fun, take a look at WebGL. It's really good stuff. So that said, now we're going to, unfortunately, go into the C version of that. Yes, I'm really excited about WebGL, but we're still back in the real world. I hire lots of folks, and we require them to know C. We'll talk about the fundamentals of OpenGL application development and how it moves forward.
Okay, what I'm going to go through is sort of our first OpenGL, almost said WebGL, our first OpenGL application. And as I've said, what we're going to try and do is develop a rotating cube. So we'll talk about how you model the surfaces, how you put it together, how you get color, and then we'll be able to enhance it later as we go through the course. Okay, so here's a very simplified version of how we can look at it, sort of from a programmer's point of view. And if you're working in a shader-based OpenGL, you have to produce 3 programs, each of which is a complete program. You have your application program, which will typically be written in C or C++. You'll have to write a vertex shader, which is as you'll see, in a C-like language with some enhancements. And you'll have to write a fragment processor, which is a separate program also written in the OpenGL shading language. If you look at how the data flows, another way to look at this is that what the application program's job is to really describe the geometry. What I'm going to do is say, well, I want to draw this cube. How do I draw a cube? I have to specify the vertices and how they're connected to each other, or describe the faces or something like that. So its fundamental job is to do sort of 2 things. One is describe the geometry that you would like to have rendered, and 2, describe how that geometry should look, whether it should have colors on it, whether it should be texture mapped, whether you're going to do lighting, all the things that we're going to be talking about a little later. Now, that information you can think of as really being tied to vertices. And so the first stage of what the vertex shader has to do is process these vertices that are coming along. Now, what does that involve doing? Well, obviously, it's going to depend on what you want to have done, but the fundamental things it has to do is do some kinds of coordinate conversions to get it into the kind of coordinate system that OpenGL wants to use internally, and then it has to put together the vertices into objects. So if I want to define a triangle, I'm going to specify 3 vertices, and somewhere that's going to be assembled into a triangle. Or if I have 99 vertices and they're supposed to describe 33 triangles, there's a stage where that OpenGL has to put those together. That information is then sent along to a rasterizer, which is the only part of the process that you don't control. The rasterizer is going to put things together. It's going to decide which points on the display can potentially be affected by what you have defined in your geometry. And I say potentially because the way the pipeline works is that we're feeding in geometric information. We're feeding in vertices that specify certain objects, but a later object could block that the object you just defined from view. So we always want to have the idea that there are potential pixels. Pixels are the picture elements you display. In the OpenGL terminology, they're called fragments. So think of a fragment as a potential pixel and all the information that's needed to display that pixel, for example, its color, and that passes through the pipeline, through the rasterizer, which generates the fragments for an object. So if I'm dealing with one triangle, I send in 3 vertices, just 3 points in 2 or 3 dimensional space, and what comes out of that rasterizer are the locations of all of the pixels or fragments that go inside of that triangle for the display you have. Then they can be processed. I go on to fragment processing, which is described through a separate program called a fragment shader, and that fragment shader operates on each fragment. So another way to look at this is that a vertex processor is a program that acts on every single vertex that comes down that pipeline. A fragment shader is a program that operates on every single fragment which comes out of the rasterizer. And what can it do to those fragments? Well, it can color them, it could add texture to them, you will deal with talk a little later about things like hidden surface removal, how do you tell what's behind or in front of something else, and all those things can be dealt with at the fragment processing shade. And eventually you get pixels which go into the frame buffer and will be displayed on your device. Okay, so in OpenGL, as we said, that you have steps that you have to take. You have to create these three programs, the application and the two shaders, and if you go on to more advanced things, you're going to be writing a tessellation shader and perhaps a geometry shader, but minimally these three programs. We create what are called buffer objects that involve taking the data that's defined. Now, where's your application running? Your application is running on the CPU of your computer, so we need to get that data over to the GPU, which, as Dave pointed out, can operate at absolutely incredible speeds. So the job, you can think of the job of the application program is to specify your geometry and get it over to that GPU where it's actually going to be processed. So those are what buffer objects do. We put the data in them, we get those buffer objects onto the GPU through our application. And we have to connect a lot of things together because you have these three different program objects that are working on different things, but they're sharing information. So you might have, for example, consider a color. A color might be specified in your application, but it might have to get over to the vertex shader to be manipulated or perhaps just carried over to the fragment shader. So how do these different programs know about each other? And that's something we're going to have to talk about, is how the information about variable names and linking everything together is done. And we'll talk about it. And finally, when all of that is done, the rendering is essentially one line that just says, draw this stuff. Okay, so it's getting data set up in the application, moving it over to the shader, and then just rendering the whole thing with usually a single line in your program. Okay, so a couple of problems come up. We said that OpenGL is really concerned only with rendering, and it's system independent, it's Windows system independent, it's platform independent. But the problem is we work on real platforms and we work with different operating systems, and somewhere along the line those things have to come in. Now, there's some available software for each system that you can think of it as the glue that ties the system dependencies to OpenGL. And as you might think, it's different for each system, whether you're running on a Mac or you're running on Windows or you're running on your cell phone, it might be different. But we really want to stress, and especially those of us who teach a lot of this, we want to say, hey, look, we don't want to talk to you about, oh, this is the way you do it on Windows and this is the way you do it on a Mac. And so we have a few libraries that help us get around that. The principal one for many years has been GLUT, which was created by Mark Kilgard, who's now at NVIDIA, was at SGI, which is a platform-independent system that will do the basic windowing and input operations, the kind of operations that are shared among all the platforms that you might work on. So it will open a window for you, you can change the size of the window, you can get mouse input, you can get menus, the basic kind of things that are in common. It doesn't guarantee they're going to work at the highest speed or use every capability of your local system, but it'll allow you to write code that will be transferable to any of the other standard systems, and all you have to do is recompile it. So we're going to use GLUT. Actually, we're going to use a version called Free GLUT because Mark hasn't worked on this in many, many years, but it's been incredibly valuable, and people have updated it with a couple of versions that you can easily get off the web. Free GLUT is the one we've tended to use. There's another one, GLFW, which some of you might want to use, all of which are compatible with the latest versions of OpenGL. So they'll handle simple input and the basic things that you need to do to get a window in which you can render. Okay, so now there's a few other little uglinesses that come up, and we're going to try and get rid of them real quickly. One of which is that there's a lot of complexity in really how things are done in an operating system and how it handles functions, and especially for me when I try and run things on Windows, because you got libraries, you've got DLL libraries, and tying all this together with external packages can get very, very complicated. You need entry points and things. Well, there's a library that's very, very helpful called GLUE, which is called the OpenGL Extension Wrangler library. And it also deals with things that extensions, as Dave mentioned, is a lot of things start off as extensions and then become part of OpenGL. And their function names have these extension tags on them. Well, the GLUE library will take care of it. It'll be aware of what extensions your system supports and the names. And so GLUE turns out, especially for those of you who work in Windows environments, and actually it's very, very helpful in Linux environments too, is to use the GLUE package. So if you're really going to run OpenGL, what you need is an OpenGL library. You need, generally you will need to use the GLUT library for learning. And if you're an expert on your own operating system and its windowing package, certainly you can use that. And then there's these little packages to tie that together to OpenGL. But generally, most people will start with GLUT, GLUE, and OpenGL. Okay, so now let's go and actually talk about how we do things in OpenGL. So the fundamental entity for defining all of the geometry that we work with in graphics is a vertex. And a simple way to think of a vertex is it's a location in space. And it has coordinates in space. Now, so a triangle is specified by 3 vertices, and that was the definition for a long time. Now, in modern OpenGL, the definition is expanded a little bit to say that a vertex really is a little more than that. This is sort of going away from the fixed function pipeline. In the fixed function pipeline, you had a vertex function, and you had a color function, and you had a texture coordinate function. The more modern terminology to say is a vertex is an object that has certain attributes, one of which is its positions. So what you used to think of as a vertex is now the positional attribute of the vertex. I'll go back and forth saying, usually if I just say a vertex, I'll say that's it always has a position attribute, so it has some location in space. It could also have these other attributes, its color, which can be defined when you define the vertex, or maybe defined later in one of your shaders. It can have texture coordinates. Later when we talk about lighting, we'll talk about the importance of normals, so that could be another, the direction that the surface is at the location you're talking about. That's another attribute you might want to add. And one of the reasons that we really like having this modern OpenGL is these attributes are up to you. So if you're dealing with an application where, for example, you're dealing with temperatures, you can make the temperatures be just another vertex attribute like any other vertex attribute and be treated like that. If you're dealing with a flow problem, then at every point in that flow, you have a direction of flow. That can become an attribute. So this is a very flexible mechanism for those of us who program applications. Okay, now the how they're stored may be a little new to any of you who haven't done graphics. They're stored in 4 dimensions, which is called the homogeneous coordinate representation. Generally, the first 3 coordinates are the x, y, and z in some space. That's another one I should touch on for a second. What OpenGL lets you do is work in your own coordinate system. So when you're working in your application, your C, C++ program, and you specify a vertex position, you can specify that in the coordinate system of the problem. You're not worried that OpenGL enforces a particular coordinate system on you. It doesn't. You get to work in the coordinates, the natural coordinates for your application. Now, the unnatural part at first is this idea that you have a 4th coordinate, W, and let me you'll see more of why this is important a little bit later, but what it lets you do is give a common representation to both vectors. Vectors, if you think back to physics, vectors have direction and magnitude, but they don't have position. Position is something else. They're different physical quantities, and what homogeneous coordinates lets you do is represent both within the same system. Generally, what will happen is that if it's a point, the W will be 1. If it's a vector, the W will be 0, and then you have a very elegant way that transformations work out that we'll talk about a little bit later after the break. So let's just accept for now that we work in homogeneous coordinates. If you specify something in 2 dimensions, OpenGL will automatically set the z to be equal to 0 and the w to be 1. If you specify something in 3 dimensions, it'll take your x, y, and z, and by default set the w equal to 1. So you don't, in practice, when you write your programs, have to worry too much about it, but it's one of the key things that makes everything work. Now, where does this data go? The data is going to be assembled into something called a vertex buffer object. So we're going to define these vertex buffer objects in our application and get those vertex buffer objects over to the GPU. Vertex buffer objects are stored in another entity called a vertex array object. Now, this at first is going to be very troublesome. You can just simply define one. But the idea is this, that when you deal with complex objects, objects may have properties that change a lot. And one of the advantages of this, it allows us to collect a lot of attributes and information into a single object. So for example, if you think about the vertex is an object that collects all the properties of the vertex. The vertex buffer object can collect all the information about a bunch of vertices. The vertex array object can collect together all the information from a bunch of vertex buffer objects. And so it allows you to very efficiently switch between objects while your code is running. Because the thing you're trying to always avoid is having to send data over from the CPU to the GPU over and over again. What we want to be able to do is get that data over once to the GPU, and then if we have to, switch between different collections of objects in a very efficient way that doesn't involve us resending all the data again. And that's what vertex buffer objects and vertex array objects are going to do for you. Okay, now what are the kind of primitives that OpenGL knows how to render? And it's a very a small set, actually, and we can render points. So if I send a set of vertices over to a GPU, I can say, let's suppose I send n vertices over there, and each of those vertices has a position attribute. How can I render them? Well, I can render them, if there's n of them, I can render them as n points. But those same endpoints can define a number of other possible things, and the ones that OpenGL is willing to do is say, well, I know about line segments. I can interpret those n vertices as n over 2 line segments with each successive pair of vertices defining one line segment. Now notice that will leave gaps. So the first and the second will define that first line segment. The third and the fourth will define the second, but there's not necessarily a connection between the second and the third. If you want to do that, you use something called a line strip, which says if I give you n vertices, it's going to define n minus 1 line segments, the first one between the first and the second point, the second one between the second and the third. And if you want to connect them all back, all you do is say, hey, take these n line segments and make a loop out of them. So always connect the last point back to the first point. That's called a line loop. It's not, a polygon is different, as we'll see in 1 second. Now, OpenGL, the modern versions, only want to deal really with triangles. And there's both mathematical and practical reasons for wanting to do that. Any 3 vertices will always define a triangle. You don't have any special cases to worry about. Even if the 3 vertices all lie on the same line, you can consider that a degenerate triangle, but your hardware won't fail you on that. So if you say you want to render these n vertices as triangles, what OpenGL will do is take the first 3 and render that as a triangle, take the next 3, render that as a separate triangle, and so on. Now that, if you're dealing with CAD problems where you're just describing surfaces, you can say, well, I want to break up this surface into a lot of little triangles. And we're talking about rendering hundreds of millions of triangles per second in a modern GPU. You can say, well, gee, that even that cannot be fast enough if I have all of these vertices to send over, and eventually you can worry about how much memory is on your GPU to contain this stuff. So there are some variants that really make things much nicer. A triangle strip says this: take the first 3 vertices and define a triangle with that. Then take the 4th vertex and connect it back to the 2nd and 3rd. And take the 5th vertex and connect it back to the 4th and the 3rd. So each additional triangle, each additional vertex defines an additional triangle. So it turns out to be a very efficient way of defining surfaces in CAD applications. Another way that you can do the same thing of having each additional vertex define another triangle is what's called a triangle fan. You keep the first vertex always fixed, and then the 2nd and the 3rd, and the 1st, 2nd, and 3rd define a triangle. Then each additional one is combined with the previous one and that first one. So you always have this fixed point. The way I like to think of it is if you think about a model of the Earth with lines of longitude and latitude, and you notice all the lines of longitude converge at the North Pole and the South Pole, well, that's a triangle fan at the top. You have the fixed point of the North Pole and all of these triangles radiating out from it. And so that triangle fan, if you were making a little model of a sphere, would be a very helpful thing to have. Okay, so now let's look at a program now that uses all of this. So let's do this. So we're going to talk, as I said, about a cube, and the only other property I'm going to have besides position at each vertex is I'm also going to have a color. So I'm going to have 2 attributes to each vertex. So what I have to do is initialize those data and then get them over onto the GPU for rendering. Now I also, because a cube is simple, but it's not totally trivial, because I don't want to define it in the most trivial possible way, I'm also going to have a little bit of a way of showing you how to arrange that geometry in a nice way to build a little model. Okay, so let's argue this way, that if I want to describe the cube by its faces, so that, and it's one thing to keep in mind sort of back in there, that OpenGL fundamentally likes to deal with surfaces, and that we tend, when we're working in OpenGL, to think of the objects we're dealing with as being defined by their surfaces, not being defined by that a cube is the fundamental underlying primitive. Some solid modeling systems would do that. But in an OpenGL environment, you tend to want to model things by polygons that can be decomposed into triangles, or at worst quadrilaterals. So we're saying, okay, what is a cube? A cube is an object that has 6 faces, and if we have to get down to triangles for the rendering to take place, each face is a pair of triangles. Well, and each triangle is defined by 3 vertices. So if I want to look at it that way, that it takes me 36 triangles, to display that cube, I'm going to eventually display 36 triangles. Okay. Now, to make things a little bit easier, Dave and I created, when we did the last edition of our book, we created a little package that defines certain simple geometric types, like a vec4 and a vec3. Think of it as a vec4 as a 4-element array in C++, and allow you to manipulate those kinds of things. Now, one reason that was behind that you'll see a little bit more when Dave talks about the shading language, is that we said that the shaders are written in a language called GLSL, which is very C-like with certain additions. And the additions are that it defines some additional fundamental types, like matrices and vectors of 2, 3, and 4 dimensions. So vec2, vec3, and vec4 are really the building blocks of the shading language. And one reason that Dave and I wanted to create a library on the application side, the C and C+ side, is that the algorithms that we were doing on the application side would look very much like what you could do in the shader, because one of the things you'll learn is that you're going to have choices to make. Do I do this operation, for example, lighting? Do I do lighting in the application? Do I do it in the vertex shader? Do I do it in the fragment shader? And by having these types, it'll be very easy to experiment and develop algorithms in one place, put them in another place, and see what the performance is like. So we created this little package. It's on the web. You can download it. And then you can, if you want to have trouble saying, well, if you're dealing with a vec4, but you're talking about a color, well, you can use a type def and just type def color 4 and point 4 to vec4, and then your code will look beautiful. It'll look, colors will have the name color, and points will have the name point, and the code will look very nice. So you'll see that as we go along. Okay, so we're going to initialize a vertex buffer object to get our data ready. We said we had these two attributes, the position and the color, and I'm going to create two arrays to hold these data. Okay, so I'll create a positions array to hold the 36 vertices and a color array to hold the 36 colors. You'll see what'll happen when each vertex has a different color when I run the code for you. Okay, so here's the data. We're going to do a little thing. We're going to have a cube of side length 1. It's going to be aligned with the X, Y, and Z axes just to make life a little bit simpler. And we're going to define them in 4 dimensions so that the W component is going to be 1. We just automatic. Now, I could have said 0.3 positions 8 and made each of those a 0.3 and left the 1 off. OpenGL doesn't care. If you don't send it the 1, it'll put the 1 on for you. Okay, if you send it a 0, it'll keep the 0. So it's pretty flexible that way. I'll do the same thing with the colors. Colors are represented in a red, green, blue system, so where 0 means none of that component and 1 means the maximum value of that component. The 4th component is called the alpha channel or the A value, and it can be used as for opacity, where 1 would mean that the surface is opaque, 0 would make the surface transparent. It's an extra facility in OpenGL that you have to turn on called blending. As if you don't turn on blending, that 1 is going to be ignored, but so it's there just because we're doing everything in 4 dimensions in this example. Okay, now I'm going to set that up. I'm going to have a function now. I'm going to build, so here's the modeling part. I'm going to say, well, I can just list all these things out, but I want to use a little bit of structure. So I want to say, well, if I'm dealing with a cube has 6 faces, so why don't I write a little function called quad that defines each face of the cube, and I could then just pass in the indices of the vertices. So let's do it that, or let me say this slightly differently. I give you a cube. How many vertices are there on a cube? How many unique vertices are there? 8. So there's really only 8 vertices. So really I can think of, instead of doing everything 30, even though I know I'm going to have 36 vertices in the end, they're just different combinations of those 8 vertices. So I'm going to use some indexing to make this a little cleaner. So what I'm going to do is make an array. I'm going to make it out of quads, and I'm going to pass into the quad the number of the vertex in order. I'm going to pass it in the vertices that make up that quad. So for example, if one face has vertices, the first vertex 0, vertex 1, vertex 2, and vertex 3, I would call quad of 0, 1, 2, 3, and so on for the other faces. So what does this function do? It puts into the array the color and the position of that vertex. And it also increases the index because I'm in a more general application. I may not know that there's 36 vertices or a fixed number. So every time I put something in that array, I'm increasing the index. And in the end, it'll come out to be 36 for this one. So here's now the cube. The cube now is described in terms of the vertices. And the vertices are here's the numbers. If you look at a little picture of the cube and number of the vertices, you'll get something like this. Now, there's a little trick in here that we haven't gotten to yet. and I should talk about it right here, is if the 4 vertices in order that define this face are A, B, C, and D, OpenGL only deals with triangles. So what am I going to do here? I really want to define 2 triangles, not just the face. So if I say the 4 vertices are A, B, C, D, I can take the first 3, A, B, C, assuming they go around in a little square. So A, B, C define a triangle, but then I need to define a second triangle. Well, how about going from A, the first one, diagonally across to C, and then down to the 4th vertex? That's the second triangle. So if I want to do that, then within this little quad function, I actually define 6 vertices, or put 6 elements into those arrays, A, B, and C, A, C, and D. Now, some of you sitting there saying, wait a minute, he just talked about another way of doing this, which is, why don't you use a triangle strip, or instead of using 2 triangles? And you could do that. You can define this if you get the ordering right. So here's a little exercise for you to do. How would you do this with either a triangle strip or a triangle fan? And if the answer is, in either case, you can do it by putting 4 vertices into the list instead of 6, but be very careful of the order. Okay? So this is a simple example. We don't matter, but if you're doing a big, serious problem, you really want to do it with triangle strips or triangle fans if you can. Okay, going on. So here's the function. Here's the color cube defined by the indices. That's very simple. So now we've formed the 2 arrays. Now we have to get the arrays over there. How do we do that? Well, we need a vertex to specify a vertex array object, and minimally a vertex array object and a vertex buffer object. So we can, usually what we'll do is we'll let OpenGL keep track of that and keep track of which indices are available. These indices are basically just integers to refer to them with. They're just identifiers. So we can ask for some names or ID names or integers by just calling gen vertex arrays and tell it how many you want. Okay, so it'll generate unused, it'll keep track of how many, because you can create these objects and destroy these objects. So that will be a very safe way, instead of assigning a number yourself, say, hey, give me some number that's unassigned. So you'll get back, if you ask for 1, you'll get back for 1. If you ask for 10, you'll get back 10. Now, the other thing you have to do is there's a notion in OpenGL of thinking of it as a state machine. That what happens, think of it as a machine that you put in certain specifications about your colors and your locations and everything, and its output is an image. And inside is this machine. And a machine, what it does depends on the state of the machine. So you can think of a lot of what you're doing as setting up the state of this machine so that when you push the button that says render, it's going to render given that present state. And there's a lot of things in OpenGL that are like that, and one of which is, what is the present vertex array it's working on? Because you may have defined a bunch of them. That's the idea, to be able to switch among them very easily. So what you do is you use the bind function to say, this is the present array that you're working on. This is the one I'm talking about. And until you do another bind, that is all function calls that refer to vertex arrays are going to refer, or buffer arrays are going to refer to this one. Okay, the same thing is going to be true with a vertex array object. You're going to bind it, you're going to get as many as you need, you're going to bind the one you want to talk about, leave that alone until you want to switch it, and switching it just requires another call to bind. Okay, so it's very, very simple. If you simply want to do our little thing where we have one vertex array object and one vertex buffer object, we just need one identifier. So I say generate vertex arrays. I only want one, and put it in an integer VAO, and then bind it to make it the present vertex array object. Okay, that's simple. Vertex buffer object will be pretty much exactly the same. Bind the now, the vertex buffer objects, there's a couple of kinds of them. And the only one we're going to talk about here is called a GL array buffer. GL has a number of parameters. They're pound defined in an include function that'll be something like gl.h, so you don't have to worry about magic numbers. But what we want in our example is to generate a vertex buffer object that's of the type that's going to include an array buffer. Let me give you one more example. Another way of doing this program is to do it almost exactly the same, but to do what's called an element buffer. And then you draw by giving it the element numbers instead of the vertex, instead of giving it vertex numbers. It's almost identical, but the point here is that there's a couple of ways that OpenGL lets you do things. We're going to just do GL array buffer. So that's the first parameter in buffer date. We bind the buffer, then we're going to ask for a buffer in gen buffers. We're going to bind that buffer, and then we can send the data over. Okay, let's see how that. So here's the whole thing sort of put together. Okay, so we get a buffer. We only need one buffer, for example. It's an array buffer. We bind that buffer. Then we're going to send data over. Now, there's a lot of variety of how you can send the data over that depends both on your application and how your GPU actually works and how it stores its information. But so what we're going to do here is let's look at that middle line there that says, here it is. Let me see if I can. Okay, let's look at this line. What I have to do is tell it how much memory do I need on the GPU. Now the idea is we're getting the stuff finally over to the GPU. This is the type, how much memory I need. Static draw has to do with a really good GPU can organize its memory in very efficient ways. If I'm going to send it over once and never send it again, versus an application where I may be sending data over and over again, the GPU itself might say, hey, well, if it's repetitive data, I want to store it this way instead of this other way. And so we're only sending it over once, so GL static draw is fine for us. And the null here says, I'm not sending anything over. All this is doing at this point is reserving the storage. Okay, so now on the GPU, in its memory, I've reserved enough data for the positions and the colors that I just set up, and now I can send them over separately. Now, if I had put something here like the array name, I could send it over in this one shot, but I want to send it over in two shots because I'm sending over two separate things. I'm sending over the positions. Here's the amount of data I want to send over. It's coming from the vPositions array that we just set up, and it's of type array buffer. This has to do with normalization. We're not going to ask it to, no, I'm sorry, excuse me. This is where it starts. It's going to start right at the beginning of the memory that I allocated. Now I'm going to put the colors right after that. So I'm going to send over colors of the size of colors, and it's going to be offset from the beginning by what I just put in over here, which is the size of positions. Okay? Is that the only way to do it? No. You could have decided to interleave the data. There are a lot of ways that you can do this. You're managing memory, but here's a very, very straightforward way of doing it. Oh, you could also say, well, why are you using one vertex buffer object? And the answer is I just happened to in this example, but you could have used one vertex buffer object for the colors and used another vertex buffer object for the positions. All of these things are possible. You're getting a lot of flexibility in how OpenGL allows you to do things in modern OpenGL, and they can have a major impact in the efficiency of your application, again, depending on your particular application and how your particular GPU functions. Okay, so now the data is sent over there, and now the next problem is connecting everything together. How do we connect the data to the shaders? I haven't talked about the shaders yet. I have data now I've been successful in that. I've got data now on the GPU. Now I need to manipulate it, and I need some connection for the shader to understand the positions were positional data, the colors were color data, and connect variables in the shader to variables back in my program. So there's a function called GL attribute location, which gets me that information about these attributes that I've sent over. So here's another little piece, and these parts are pretty standard. It may look ugly at first, but they're fairly standard. So we have to associate shader variables with the names that are in our program. Now, suppose what we're going to do is, and again, let me use the pointer here. Suppose in my shader, which we're going to get to in a minute, I say that the name of the variable in the shader is vPosition. Now, the way that this is going to work is that I'm going to develop what's called a program object, which is a container object in my program, in my application, that has my shaders inside of it. Okay, so I define shaders, I dump them into this thing called a program object, which has a name. Okay, so for that, and again, think about state. There's a present program object that has your shaders in it. But later I might want to use some different shaders. So I'll have a different program object, and I could switch between the program objects, and instantly I'll be using this other set of shaders. Again, more flexibility. So I have a program object that has my shaders in it, which we haven't yet gotten to talking about how we set it up. And I use the name in my shader called vPosition, and I'm going to get where it is, and I'm going to set it up to something called vPosition in my application. You don't have to use the same names here. Dave and I have been adopting this convention where we're using the same name to lessen the confusion, but at some other level it may be confusing at first, but I can call this anything I want, because the one on the left is a variable name in my application program. The one on the right is a name in my shader program, so they're independent. This is just saying when you see this one, you should refer to this one. But we find it more convenient to use the same names. I do the same thing for the color attributes. vColor is the name in the vertex shader, and I'll use the same name over here where for the returned location. I have to enable those arrays. They can be enabled and disabled. Attributes, sometimes you may be wanting to use them, sometimes you won't. You're always going to want to use the positions, but you may want to use constant colors and later switch over to using computed colors that were computed with some lighting model. So you can turn attributes on and off, enable and disable them. The data is still there. You're just saying when I render, these only render using the ones that have been enabled. Okay, and finally, I want a pointer to, I have to tell the system what format they're in. So this is saying that vColor, similarly up here, they're 4-element arrays. They're of type GL float. I'm allowed, if I want, I'm allowed to normalize those automatically, which we're not bothering to do. And there's an offset here which says, where are they located? Well, the positions we said came first, and they're followed by the colors. And so when I talk about the colors, I'm going to offset them by the size of positions. Okay, so this is just a handy little mnemonic that Dave uses to make it clear what you're doing. Where in the buffer is this data? So you're telling it you're telling the GPU where the data is in the buffer and what format it's in, and you've given it a name. Okay, so now you're sort of ready to actually do something with the shaders. Now, what happens after you do the shaders? We're going to get there. How do you draw this stuff? Now, all of that was kind of ugly. Dave likes to call it the plumbing, and it's, you got to do the plumbing to make this happen. But what's going to happen eventually? You're going to draw. Here's the good part. When you're finally ready to draw, that's it. The data's there. It knows everything about the data. It knows where it is. It knows how the things are coupled together. And all you have is one function that says, draw those arrays as triangles, starting with the first one, the 0th element, up to the last one. That's it for actually drawing the stuff out. If you want to draw it as points, you do GL points. If the data were organized as a triangle strip, you would have triangle strip 0 up to how many vertices define the triangle strip. So eventually, once you've gotten through this plumbing, which is the same in every program you're going to write, it becomes very, very simple to do. Now, what happens next? Well, when you run that GL draw arrays function, it's going to initiate a vertex shader instantiation for each vertex. Okay, so now you're starting to see the pipeline taking effect. Everything we did up until now set up the pipeline by putting the data there, describing the data, describing where variables were. Now we're ready to go. So we say, draw arrays. Now, for every vertex, the vertex shader is going to run. The rasterizer is going to produce fragments, and for every fragment, the fragment shader is going to be run. Okay, now the pipeline is really in action. So, let's see what, oh, sorry. Okay, so Dave will now talk about the shaders, which we haven't gotten to yet.
Excellent. So I like Ed going, hey, this is something that Dave cooked up. That buffer offset thing is not entirely my idea. It's just a macro that basically takes the value that's passed in and passes it along. But it really signals, hey, you're using buffer objects, and this value you're passing in there isn't a pointer. One of the things you'll find in OpenGL is the API hasn't been able to evolve as perfectly clean as we might like, and so that really accepts a pointer to some data memory, but that's the old way of doing it, and we don't accept it anymore. So we try to make it very clear on that. On the plus side, I am sitting here going, oh, look at that beautiful code, because like I'm influencing an entire world of how you should accurately write code. Anyways, shaders and GLSL. So you've seen a whole lot of code. It turns out that there's probably about 20 functions you just learned, and most OpenGL programs will leverage those 20 functions time and time and time again. As Ed mentioned, you'll create a vertex buffer object, collect those together in a vertex array object, you'll define variables, set up the plumbing, and so on. Everything he just discussed. And modern OpenGL programs are just repeating them ad nauseum because the draw becomes, as he pointed out, a single line. Now, that's all on the API side. Shaders are where all the magic happens, and so I'm going to give you a real brief whirlwind tour of GLSL, which is the shading language that our shaders are written in, its capabilities, a couple of gotchas, and then we'll work through more examples after the break of actually putting all this structure together. So, to begin with, right, this is talking about a programming language. GLSL looks a lot like C, actually, like C, C++. We don't have templates, we have overloaded operators, you can't make your own. It's like watching paint dry, right? It's a language. It's got semicolons at the end of things. We all go from there. But what's important about it is it has a sequence of types, and some of these may look familiar, just as Ed pointed out, because we try to make the education of this very easy, to make types that exist in your application map over to the identical types inside of your shader. Now, shaders really manifest themselves as, at the end, a character string that you pass into the OpenGL API. You might store it in a file, you might generate it on the fly, but it's a sequence of ASCII characters that will stick in a function to tell GL to do some stuff. Hold on to that thought, because there's a lot of fun coming with that, and that's not sincere fun, that's sarcastic fun. But I get to poke at the API because I've written about this for a long time. But we have a lot of data types to help you represent your data, and this is not an exhaustive list, but it gives you a flavor of it. You, of course, have scalar values, floats, ints, booleans, and it's fully functional. You can make if statements on booleans, and I'll talk more about that. There are also vector types, because we're talking about computer graphics, right? Ed went on about a vertex is really a package of attribute information connected to a point in space. Those attributes could be single valued or they could be vector valued, and the API allows you to kind of match all that logically together. So if you have a temperature, that's a scalar value. If you have something like wind direction, will that be a vector? Or any number of other features that are inside of there. So we have a bunch of vectors that go along with that. We have a bunch of matrix types. So these are ones for square matrix. Mat2, as you might guess, would be a 2x2 matrix. We have pretty much every dimension except 1 by something, because a 1 by something is really just a vector, so we go with that. Mathematicians who don't like that idea, please stand in the back left corner. So we put all this together, and we'll show you how this operates in a second. There are operators that are logically defined, as you might see in any math class, for working with those guys. Additionally, there's some other types that may not be logically evident for the first time through, one of which is called a texture sampler. This is another piece of plumbing, and as Ed said, there's a lot of plumbing that happens here of connecting words in one file with words in another file through function calls. Given the way we had to do it, it was the best option we had. We just all suck it up and kind of do it this way. But texture samplers are a handle to another concept we'll talk later in the afternoon called texture maps. And basically, this is the way that you access one of these guys. We'll just here introduce it and say, you'll see this in shader code a little later on. Now, just to start rounding this out quickly, all of these types are constructed in a normal C++ constructor way. Now, once again, GLSL is not C++, but adopts some of the better ideas that are inside of there. So you can't actually say vec3a equals curly brace xyz. You have to kind of construct them together. You also need to make it explicit when you want to switch types. So you can't say something like float f equals int3. You actually have to kind of cast them. And this is just to make the compiler and the syntax a lot cleaner. Admittedly, it's more troublesome to do this, but it makes analyzing your code much simpler. And since these really quite often happen in real time, compilation time is a big concern in OpenGL. Now, as I mentioned before, there are logical operators, and particularly in the mathematical sense, but also you can ask if one vector is less than another, or are certain elements of a Boolean all true or all false. So there's a rich set of operators that go through here, including ones for operating on matrices and vectors, which are used quite often. The fundamental crux of, we'll talk a lot on the vertex side about manipulating vertices, and quite often that's taking a matrix and multiplying it by a vector. And you'll do that many, many times. Now, simple enough. If you don't know how that goes, pick up a book on linear algebra. The rest of you can kind of run away from those horrific years in high school when somebody tried to explain why matrices and vectors were important. What is important, and you might have to blow the dust off your brain on this part, is the order of matrix and vector multiplication is extraordinarily important. Right? In OpenGL, you always want to multiply your vectors on the right side. I'm terribly dyslexic, but that's the one over, well, from your vantage point on this side. So if you see this bits of code, right, b equals a times b, a being a vector and m being a matrix, and on the bottom, c equals m times a. Syntactically, that's perfectly valid, and GLSL knows exactly what you're trying to do. For the b variable, right, you're taking a vector a and multiplying it on the left-hand side of a matrix. Perfectly well defined, probably not what you want. And quite often this is a really difficult bug for people to figure out in their shaders, because you're doing something perfectly legal, but it's a pure logic error. Really more often what you want to see where you're multiplying your matrices or your vector on the right side of the matrix. Important point, I'm dwelling on it because really there's nothing wrong with your code. It'll run perfectly fine, it just ain't right. And if you look at that, it looks perfectly legit. So there you go, suitably worn, moving on. One of the nice things about all of these vector types is they provide you accessors. In C, you've got one way to access the elements of array, and that's using square bracket notation. Now, we're doing computer graphics, we have a lot of kind of logical attachments to data. For example, a position. If I ask anybody, hey, what's the coordinates of that point? You go, well, x equals this, y equals that, z equals that. I think we'd all probably agree on that. So GLSL actually enables those kind of notations that go along with it. So for example, if you have a vec4, which is the largest vector you can have, you can always use square brackets, and as I demonstrate down here, you could say v square brackets 1, and that'll give you the second element. It's all zero-based indexing. But if you're working on, say, positional data, x, y, z is the logical choice. Conversely, if you're working with colors, RGB is the right choice. So we have what are called named components that allow you to access data in particular ways. Now, I apologize, there's one small error on this slide. You'll note we have XYZ, perfectly fine. RGBA, sounds like a color to me, that's very good. STRQ, so the R in here is an error. That should be the letter P. And those are for texture coordinates, and we'll talk a little bit more. My apologies on that. But these allow you to work with data in a more logically concise way. There's no magic about it. If you say X in one case, or more specifically, you say v.y is exactly identical to saying v.g, or in this case, v.t. But if you read your shader code, most people will go, oh, XYZ, positional stuff, ST, texture coordinates. So it's kind of the common language that you want to do for that. Now, one of the other really powerful parts of having these named things is something called swizzling. And this is the ability to allow you to take and exchange data positions inside of your data objects. So for example, if we have two vec3s, A and B, and we want to swap the x and y coordinates, you can just write the following logic that says a.xy will receive the values b.yx, and in the process they'll be flipped. Almost all GPUs do this in one instruction very rapidly. You might go, well, why do I need to do that? Well, Windows, for example, enjoys using BGR as the ordering of its colors, while most images out on the web actually use RGB. So it's a nice, convenient place to do those kind of operations. It's also powerful if you need to populate a vector by repeating a value. You can repeat the letters inside of there, and it'll just expand it out. So it's a very powerful grammar for being able to manipulate your data. Now, moving on. You'll find this concept here where a shader is an object that works on, in certain cases, a vertex, in other cases, a fragment. Vertices, well, what in this conversation is vertex shaders, but vertices work in all the shaders that are to the upstream of the rasterizer. So that'd be your vertex shader, your geometry shader, and your tessellation shaders. Conversely, fragment shaders work just on fragments. Now, it used to be the case that we called them vertex attributes, and you saw that the routine that Ed mentioned that was get a trib location, and a trib is something that appears in a vertex shader. That was the original part of the language. It's a little old. As we added more phases into more shaders that we were able to chain together, we needed to update the language slightly. And so we use these values called in and out. In is data that gets put into your shader, and out is data that you send out of your shader. These are kind of like functions that use a lot of global variables, and I'll show you some examples in just a moment. But keep this in mind. In is data that comes into the shader, and in some cases that comes directly from your application. So like as Ed had just talked about, you set up your vertex buffers, and when you draw, let's say you have a vertex buffer that has 3 vertices in it. When you do the draw on, if you draw all those vertices, the vertex shader will be run 3 times, one for each one of those. And each instance of running, there's some global variables in the shader that will be updated with the new vertex value to allow you to do the processing. It kind of makes sense. They're not passed in as function parameters, but we'll talk a little bit more about functions and those pieces. The global element kind of matches how you might think of working with this if we're seeing you wanted to pass it around through different modules. But hang with me, I'll show you some more examples of that in just a moment. The other one we have are what are called uniform variables. A uniform variable is one that doesn't change when you draw a geometric primitive. Now, let's think about what I just mentioned before. Let's say you have a buffer with 3 vertices. When you draw those, the vertex shader is run 3 times, and each time it's run, it gets a new vertex. However, a uniform variable is just a constant that's run, that it remains constant across all invocations of that vertex shader or fragment shader. You might pass a constant color inside of there or some properties that apply to all the data in your scene, right? You're allowed to change vertex values and pass any attributes along with them as much as you might like, but there's kind of a data expansion problem. If you have 1,000 vertices and you want to paint them all red, certainly you could do what we demonstrated initially, which is create 1,000 positions and 1,000 colors, and the positions will all be different, and you have 4,000 bytes of red. That's not very exciting, nor is it very efficient. Uniform values allow you to kind of make concise little statements about how it all fits together. Some of the examples we use a little later, like a time value that is used across all your geometry, right? You're playing a game, characters running around, bullets flying, airplanes, they're all living in the same time space. So you might pass a uniform value in that's time, and that's used to process all the values that are inside of there. Other values that come through, we'll see in the next section called transformations that are used to affect all the vertices in the scene. We'll see how this fits together in just a moment, but hang on to in, out, and uniform. Of course, there are a lot of functions, right? This is computer graphics. You break out your protractor and your ruler and you draw some stuff, or you whip out your sines and cosines and go nuts. Right? All of the kind of standard functions that you might like to deal with inside of a shader are available inside of GLSL. Things you use quite often are things like normalize, which will take a vector and make it unit length, the matrix multiplication kind of features that go in there, and some generators for making various matrices, doing trigonometric functions. And additionally, you can write your own code. GLSL is a structured language. It has functions that are able to take parameters and return values back. So you can write good code. And so we'll show a couple examples here in just a moment. Now, there's one other part that goes along with this. Some of the values that are some of the variables that are used inside of shaders are implicitly defined. GLSL says you must fill these values in for the system to work correctly. The most important of them is listed at the top of the screen, which is GL_position. This is used in the vertex side of stuff to feed the rasterizer, and you have to write this value. And it turns out it's written in every shader stage. Now, in this course, we're concentrating on vertex shaders, but there's a GL position variant in geometry shaders and a GL position variant in tessellation shaders. In vertex shaders, it's just GL position, and it must appear somewhere in your shader on the left-hand side of an equal sign that you put values into it. There are a couple of other values, GL_frag chord and GL_frag depth, that are available only in your fragment shader. GL position only available in vertex shader. The frag ones only available in the fragment shader. They give you some additional information. Frag chord says which pixel inside the window am I working at. going from the lower left-hand corner and gives you a 0, 0 indexed 1 for that. Really quite useful for doing image processing or places where you're doing per pixel operations. Frag depth gives you the depth of a pixel. We'll talk a little later about depth buffering and some of the features of it. This allows you to kind of play around with those values. You don't find that getting used very often. Frag chord a little more commonly. However, you'll see GL position quite a bit. So here's a really simple example that we're using in the cube example that Ed was talking about, where we process those 36 vertices and use those to feed the rasterizer to go off and do the fragment processing. So this is pretty much, it's a reasonable shader. It's representative, it's functional, and you actually find out that, you know, this is the boilerplate, and you add a lot of more accoutrements to it, but it really is one of the fundamental pieces. So at the beginning, you specify the version of your shader. Not strictly required, but a very useful thing. So in this case, we're writing a shader that's to be used with OpenGL version 4.3. The shader version you can see is 430. We just multiply by 10, remove a decimal point. If you want to use 4.2, guess what? There's 420 and so on and so forth. Then we have our in variables. So these variables will be populated by data coming in from the application. Now this is a vertex shader, which means the data comes from the application and goes into the vertex shader to get processed. We'll see other cases where the data doesn't come directly from the application, but derived from the operations of the vertex shader. So Ed and I try to be consistent about matching names. So you've seen vPosition and vColor several times, right? The V stands for vertex attribute, position and color gives us some of the ideas of what's in there. Because this is a text file that gets fed into a compiler that exists inside of an API. Stop and think about that for a second. You'd never do that, right? You'd type make on the command line, or you'd press F7 in Visual Studio, and you'd build some stuff. We don't have that luxury because we're talking to a computer graphics API, so we do some other stuff. But these values, these names that are in here, this shader is parsed and that string is reserved. And if you remember a little while back, a couple of slides ago, Ed demonstrated a function that takes a string that said vPosition and returns something back. That's the plumbing part. We need to connect the application, find reference to the value in the shader, connect them together, and then start sticking data into it. So assuming you have all your plumbing set up, data will flow into there. And the results will flow on this outside, right? So data goes from the shader out of out variables. So here's our actual function. It's pretty simple. The first one just takes the vertex color and copies it into this output color. And you go, why? That's almost wasteful. Why would we need to do that? That's what's called a pass-through attribute. And all it's doing is taking vertex data and passing it on to the rasterizer. Now, what's important about this is this color will be what's called interpolated. Let's say we're drawing a triangle with 3 separate colors at each corner of it. The color will be interpolated across it, smoothly shaded. So if it's red, green, and blue, it'll be red in one corner, green in another, and blue in another, and smoothly shaded, smoothly shaded across that. The rasterizer takes care of that, but it needs to know which values that are going to be operated on. That's the significance of out here. The other part is this last piece, and you've heard me mention this. We have GL_position. And in this case, we set it equal to the vertex, incoming vertex position. Once again, very simple thing, and it turns out we're using a few tricks to make the shaders very simple to show some information for the purposes of education. Normally, that line would be considerably more complex with a lot of matrix multiplies inside of it. Nonetheless, that takes our vertex position, puts it into this output variable GL position, which OpenGL, or more specifically GLSL, automatically allocates for us. So hopefully that's fairly simple, but let me show you how the data flows through the other side of this. Now, you've heard our pipeline has 2 shading stages that we really need to be concerned with, our vertex shading, our fragment shading. Vertex shaders process geometry from the 3D world and figure out where to put it on the screen, which pixels kind of need to be lit up. That's actually the job of the rasterizer, but your vertex shader primes that part of the pipeline. The rasterizer figures out literally which pixels on the screen need to be updated, and for each one of them, we'll fire the current fragment shader for the set of geometry that goes in. So in this case, we have an in value, right, and the color that was on the other side gets put into there, and we have an out value. In this case, we call it F color for fragment color, because we're really inventive. And in this case, there's nothing really, I mean, the shader's hideously simple, but oddly enough, you use things like this quite often, where the fragment color is equal to the color you see here. The magic of this is the color you see here is not the color that came out of the vertex shader. It's been interpolated and adjusted by the rasterizer. And so there's a whole lot of work that happens in between here for preparing these kind of values for you. It turns out almost any value can be interpolated by the rasterizer. In this case, we're doing a vector of colors, but we'll see a little later example of using something called a lighting normal for doing lighting. Our texture coordinates will be interpolated. Heck, you can even interpolate matrices, which you might do for skinning operations and some more advanced gaming techniques. So that's the source code that you need for your shaders. Sadly, we're not quite finished yet. I like this slide because it's got a lot of stuff on it, right? All of you write code. Some of you write it on Windows and you use Visual Studio presumably, and you press a button and compilation happens. Some of you may use Macs or Linux, right? Macs uses Xcode or Linux, or some of you might be old dogs like me and you use a facility called make. And there's a compilation phase and there's a linking phase and there's a glory in using a compiler. We put that in a bunch of function calls for your convenience. This really is set to model the process of developing source code. It looks kind of wacky, and indeed it is, but hang with me. GL create program is kind of like allocating a little bit of disk space. Hang on to that thought. But you have to do that first. The rest of the sequence here is like making a source code file, compiling it into an object file, and then using that object file a little later for linking. Anybody who writes code that isn't interpreted, so, well, even if you're a Java programmer, this happens, but if you're doing Python and Perl, well, you kind of skipping some bits of this. But if you're C++, Fortran, Lisp, JavaScript, any of those kind of things like this are occurring. In the context of OpenGL, when we need to do this, we call GL create shader, and basically that's like creating a source code file. We populate that source code file by calling GL shader source. Now, you remember earlier on I said a shader just manifests itself finally as a string of characters that you pass into OpenGL. Well, that's the routine that takes that string of characters and gives it to OpenGL to compile a little later. The next step in this phase would be compiling that file, which you call a GL compile shader. That one runs a bona fide compiler. It does optimization. It will do all the fancy techniques, constant lifting and optimization to really tune your code up to run well on the GPU. It also reports errors back. There's an error reporting mechanism, but it's not like it dumps it out to your console or something. You actually have to go in and ask for them. We'll save you that agony. But this part, it'll either compile or it'll fail. If it fails, your program will continue running, but you won't see anything. You need to have a valid compiled shader. So there's some other techniques for, you just query, did the compiler compile? If it says yes, you're good to go. If not, then you should go off and look at errors. One point to note, the errors emitted from the compiler are meant for human consumption. They're not meant to be machine processed, so you really need to go request them, pull them up, print them out to the screen, or pull them up in a text editor after you've written them to a file, and read what they say. Another fun bit is they're not consistent across any OpenGL implementation, because hardware is different, compilers are different, so you really read them and go, oh, this is entertaining, I wonder what I did wrong. But the long and short is there's a compilation stage. The last part is attach shader, and this is akin, for those of you who are compiling aficionados, it's like putting an object file in line. If you're in Windows, you go out to your link part and list your libraries and other objects should be there. If you're an old GCC kind of guy, GCC A.O, B.O, C.O equals something A.out. This is like putting the .os in there. Now, those 4 routines you repeat for every shader. So we'll run it once to make a vertex shader. You'll run it a second time to make a fragment shader. And this will all create a program. And that program actually represents basically a graphics pipeline. Now, just to wrap the process up, we've created the program, we build a shader by creating a file, populating its source, compiling it, making sure it was successful, and attaching that to the program. In order to get everything to work together, we have to do a link, just like you would at the command line. And the link takes those object files, make sure the variables match up, and the data can flow from the vertex shader into the fragment shader and down through the rest of the pipeline. This is another place where the process can fail. And if it fails, once again, your application will continue to run, but it won't draw anything because there's not a pipeline in place to do it. After link program, what you now have is an active program that's available for use. You just need to tell GL to swap it in. And there's a routine called GL use program that actually does that for you. Now, most modern applications that use this technique, principally gaming, but it could be virtually anything, will take and build all their shaders at the beginning. Build all their shader programs at the beginning. So they'll run through this loop of stuff a bunch of times and build a whole bunch of different programs. And then when it comes time to render, it's kind of GL use program, GL draw some stuff. GL use program something else, GL draw some stuff. And this is the rendering loop, and we'll see that in just a bit. Now, that's a lot of fun. You write this once in your life, try not to screw it up, you get that worked out, and then you have some code that you hopefully will never have to touch again. This has kind of been in existence in OpenGL 2.0, and it's fine. But to save you a bit of pain, we wrote a little version, and this is available at Ed's website, called init shaders, which takes two files, does all the magic. If there are errors, it'll print the results out for you and say, hey, there's an error, this didn't compile. Otherwise, the GLUint that you see here is a valid program ID that you can pass directly into use program. Init shaders takes two file paths, one for your vertex shader, one for your fragment shader, sticks them together. I also work on another book called the OpenGL Programming Guide. It's commonly called the Red Book. And that one discusses all the different shading pipelines that are available, right? Your geometry shader, your tessellation shader, whatever. We have a slightly different function in there called load shaders that's available from the book's website. Not a plug for the book, it's just some things that knows how to handle all the modern shading pipelines that are in there. This one's just set up for this course, this context of just having vertex and fragment. But you jot these things into a file, put the paths in there, and things go much, much simpler. It will fail. It'll let you know, hey, things didn't work out if it doesn't compile or link. Now, only a couple more slides to break. I'll get through these quickly, but this is part of the plumbing process. You've seen in those previous examples, we had in variables that were in the vertex shader. Those are attributes, and what we need to do is connect that value to some data inside of your application. And that process is a little baroque. It's got a lot of steps that are very simple, but logically a bit confusing. So there are a couple of things that we need to do. Vertex shader attributes need to be attached to application attribute vertex attributes. That is, when you did GL bind vertex buffer, yes, that's correct. When you did the GL bind vertex buffer, the ID of that buffer needs to be associated with the value in the shader. And we'll find that we have to go get an index for the name of the variable in the shader and do this association. We'll show how that goes in just a second. The same thing has to be done with uniforms, and I'll have an example of both of these in just a moment. There's a mapping inside of OpenGL that takes a string and maps it to an index into a scalar number. The reason we don't just skip that part and do strings all the time is string matching is expensive. And particularly, we're trying to do things fast and in real time. So, sorting GL or V position and matching that through all the variables is just a lot slower than saying, hey, stick that in index 3 and be good. Everything will run fast. So you'll see how we map all these things together. As long as your notation is consistent, everything will be fine. Just as a side note, the positions of vertex attributes are available after linking. So you have to go through of doing the create program, create shader, compile the whole thing, and do the link to be able to get those values. That said, there are multiple different ways to do that. This is what our examples do because it's the most backwards compatible way of doing things. That process has been available since the beginning of this whole process. There are annotations you can put inside of a shader for specifying these locations to simplify this mapping and to skip having to go get the variable names. We show you the most general way. It's not the most convenient, but it'll never steer you wrong. So forgive us for being Luddites, but we're trying to make your lives easier. So in order to determine those two things, there are two functions. To get a vertex attribute, you call GL get attrib location, and program is the value that came back when you either called init shaders or a properly compiled program that uses the index value that came back from GL create shader. Or, sorry, create program. It's just the number you get back there. And name, of course, is the name of the variable. This will either return back a positive value, 0, or some other number to represent what index that variable is, or -1 saying, hey, something ain't right. Either your vertex didn't, or your program didn't compile, or you put in a variable that's not there. Likewise, for uniforms, it's the same process. It's just a different tagged variable. So those names in front of it are important. So how do we actually use that? Well, here's a simple example for uniforms. There are a couple of places. If we do, for example, get uniform location, we would got this value index. And to populate that, well, there's some function, in this case, GL uniform 4F, that takes 4 floating point numbers, X, Y, Z, W, and we'll take those values and stick it into the uniform variable. Now, when that particular shader program executes, the values you pushed in here will be plumbed down and available inside of the shader. One thing that's really important that we use quite a bit, computer graphics is all about transformations. Transformations are all 4x4 matrices. All of us in here are C programmers. Anybody not a C programmer? Anybody like Fortran programmer? Naturally. Anyone doing Ada? Okay, good. We got one person who's deluded, who I know personally, and then the rest of you are straight and narrow. Long and short, C programmers, we know how this goes, right? For a two-dimensional matrix, 0, 0 is the upper left-hand corner, and then you do the farthest out index, and everything's laid out nicely straight in memory. That's great, but that's not what OpenGL does. OpenGL was written by a mathematician who said, hey, matrices are a collection of column vectors, or he was a Fortran programmer. He never came clean on that. But the long and short of it is, if you write C code and pass it into OpenGL without this little bit of magic I'm about to tell you, your world will always be kilted off to the side. Everything is spun off. You're dealing with transpose matrices, and it will make your life heck for no reason. Once again, logic error. Here's what's important. Where'd the laser pointer go? Oh, here it is. See this transpose? Right, variable name, set it to true. This routine here we'll use quite a bit. You won't see it in examples as we go on, but in your own code you'll use it. This is how you specify a uniform matrix, which we'd use like in a vertex shader. And this transpose says, hey, take this C data structure and convert it, transpose it just like you would to match the data types that OpenGL would use. It's inconvenient, it's a bit silly, and it only took 20 years to get that in there, but this would allow you to take your C code, and you can think in the normal way of C, and make it all work inside of OpenGL the correct way. So what this one does, this is a little magic. It takes, for the uniform value we got on the previous page using get uniform location, we'll populate it with 3 matrices. So that's that leading 3 here, right? So we'll take 3 4x4 matrices, that's what this 4 says, and transpose them, true. And here's the data pipe. This does a whole lot of work. It takes the data, puts it at the right locations inside the GPU so that when the shaders run and execute it, they get and receive all the correct data. I know that was a whole lot of words to describe one function call, but you can see, OpenGL functions are like Swiss Army knives. There's a lot of features inside of them. So, going to finish up the cube example. 2 slides, we're out of here, at least for a break. So here's the main part of the program using glut. Now, most of this program this part here has absolutely no OpenGL inside of it. These functions will call OpenGL, but this is utilizing glut and glue. And for the most part, the top 4 functions initialize glut and open a window and specify the kind of window we want. So we have an RGBA window, double buffer we'll talk a little bit about with the depth buffer. It's 512, and it's titled color cube. All magic. Glue init does a whole bunch of magic behind the scenes to make you write OpenGL in a simple, sane way. Otherwise, there's a whole bunch of nastiness that you have to go through, getting function pointers and things that make people's brains kind of explode. But one function makes you allows you to write really nice, clean, simple, elegant OpenGL code. So we stick that in there. Our init function is just a way that we initialize things. It's where we set up all of our data types. We compile our shaders. We build all our vertex buffer objects and whatnot. The last parts of Glut's what's called a callback-based library. So you provide some function pointers, and I'll show you these functions on the next page, that Glut will call in particular cases. The most important is one called glut display func, which says, hey, the screen needs to be repainted, and it goes off and draws your rendering for you. That's where all the work really happens. Another nice one is keyboard. That allows you to receive input from keyboard. As you can imagine, there's ways to access mice, other devices, and create all sorts of, or receive all sorts of input. So it's a rich set of functions. We just keep it nice and simple. Last bits. So here's our display function. This is what's called whenever we need to draw something. So if somebody moves the window around on the screen, it gets obscured, it gets resized, any of those pieces, this will be called. And this is kind of the shape of all your OpenGL functions. If you learn GL draw and its variants, there's GL draw arrays, GL draw elements, and then about 16 other variations that go along with it that are for advanced usage. It's not that anything you do won't be advanced. They're just special cases that may or may not fit what you're doing. But that says go off and draw, in this case, draw a bunch of triangles starting index 0 and pass that number of vertices down. And a whole bunch of magic happens. The vertex shader will be fired num vertices times. All those primitives will be collected, all the triangles will be put together by the rasterizer, all those fragment shaders will be done with the right colors, and you'll get a cube on the screen. In some ways it might be anticlimactic, but nonetheless, all the plumbing through the pipeline is all set up. And then finally, because we're working with a double buffer program, we'll talk a little bit more about that, but basically this is what makes nice clean animations, and you call swap buffer. This is the boilerplate of every OpenGL rendering function on the planet. It starts with a clear, it ends with a swap, and you call draw in between. Now, we cheated a little bit in our init, we did the use program, but this routine will basically be GL use program, GL bind vertex array, GL draw. Repeat ad nauseum. That's kind of all that's going to happen inside of here. This makes a lot of sense. This is the high performance part of it. We want as few function calls in the way. That's why we spend so much time doing all the initialization at the beginning. The last little part's just some keyboard processing. We like it when you press the escape key that the window exits, and all that's what it does.
Just as we get started again, I just want to show you, this is the kind of program we've been talking with rotation added to it. A couple of things I want you to notice, but it has a little interaction, and Dave's going to be talking about the transformation matrices now, but let me show you a couple of things. I want to turn off the rotation here. A couple of things you can notice here is first that, what we were saying about interpolating, so we passed in, this is exactly the program that we've been talking about. However, it turns out this is WebGL rather than OpenGL, but it's virtually identical, the code. But we passed in all the vertices and then as colors, and then those colors were output by the vertex shaders output and then input and went into the rasterizer, and the rasterizer interpolated them. So the vertices, remember, were all colors, like pure colors, like red and green and blue and white and black and cyan and magenta, but they're added together and interpolated across the face because each fragment gets an interpolated value of the color. So that's why you see the color blending occurring on all of the faces of that cube. And now if you wanted a constant color on each face, there are a lot of ways to do that. You could have done that inside the color array, or you could have passed in uniform variables that wouldn't change over the entire face. So you could do it. The other thing I wanted to point out on this is you can notice that they really are, these faces, even though they're flat, really are composed of two triangles. Remember when we set it all up initially, set up those array with the vertex locations in them, we set it up as two triangles. Well, you can see what happens. You sort of can see down the diagonal what's happening with the merger, and you can, on a lot of these things, and when we look at texture later, you may be able to see that even though this is a flat face for a square, it actually is composed of two triangles as far as OpenGL is concerned. Okay, so I'm going to turn it back to Dave now. So the heart of what you do in computer graphics is generally transformations. You get your data there and you're transforming it in a different way, and the OpenGL and actually GPUs are incredibly efficient because the transformations of these 4x4 matrices are built into the GPU. So essentially you're doing them as fast as you can deal with vertices. You can also transform those vertices. So let's talk about that. Now this model is kind of, you have to be a little careful here with this model. In the old fixed function pipeline, there were like 6 different coordinate systems. Remember I said at the beginning that, well, you can define things you want in your own coordinate system, and then OpenGL will take care of it. Well, at the end, OpenGL has certain coordinate systems that are defined. So for example, when you eventually put stuff out onto your display device has a coordinate system associated with it. If you're dealing with a 400 by 600 display, it's a 400 by 600 display, and at some point the hardware that outputs colors to those pixels knows that thing has these actual numbers associated with it. So somewhere in there's certain coordinate systems that are up to you and certain coordinate systems that you have to be aware of that OpenGL or the hardware are using. Now, in the fixed pipeline versions of OpenGL, they actually defined, I think, 6 coordinate systems, which you sort of see in here. And now, because the fixed pipeline is gone, you don't actually have to use these on the left, but they're actually really helpful when you do your own applications. So we're going to stick with them here with that kind of disclaimer that you don't really have to use them until you get to the middle there. But the idea is this, that you have vertex data that's defined in whatever system that you find helpful to you. sometimes the names get changed, but one word that comes, sometimes it's called world coordinates, but more often you have a coordinate system called model coordinates, because you have the idea that you build objects out of some collection of smaller objects that are defined within their own coordinate system. So for example, we tend to build our models starting with cubes and spheres and perhaps a few other objects, cones, and they're defined generally in a convenient way. So we define a cube typically, you know, its faces are aligned with some coordinate axes, and it has a default size. If we start with a sphere, we have a sphere that has a unit radius or something like that, and those are generally called model coordinates. And we apply a transformation which then takes those and a modeling transformation which brings them into the world space. So we apply a transformation that generally does three things. It sizes it to the size you really want in your own coordinate system for your application. It orients it the way you want it oriented, because maybe you didn't want this cube aligned with some axes, and then it scales it, it aligns it, and then it moves it to the place where you want it to be. And that's generally called the modeling transformation that moves you from things that are sometimes called model coordinates to world coordinates, or more generally in the OpenGL literature, it's called object coordinates. Now, the thing is that and I think the two boxes there are denoting that you may have different modeling transformations that will apply to different objects, and so you may have just data that comes in. So eventually you wind up with your geometry defined in object coordinates, and now what happens next? Well, you're taking a picture. If you look at what you're doing in computer graphics, it's called a synthetic camera model, is that what you're trying to do is take a picture. And what you're not interested in is not so much what the coordinate system that's relevant to me in my application. I want to know what the camera sees. So I have a coordinate system associated with the camera that's usually called eye or camera coordinates, which generally has a direction going perpendicular to the back of the camera out. I want to know how far things are away from the camera and how far they go to either side. So there's a transformation that's moving me from object coordinates to camera or eye coordinates, and then I'm going to do a transformation that changes those depending on what kind of camera I'm choosing to use. Am I doing a perspective view? Am I doing an orthographic? You know, it's essentially changing the lens on that camera. That's called a projection transformation. And eventually, at the end of that, you wind up into a system that's called clip coordinates. Now, why is it called? Now, that's something that OpenGL does know about. So everything to the left of clip coordinates, you get to pick it and work with it. But again, as I said, I think it's helpful to think in terms of camera coordinates and object coordinates. And the transformation that brings you into that space, into eye coordinates, is called the model view coordinates. It's the coordinate that will the transformation that will convert you from a representation in model coordinates or in application coordinates into a representation in terms of what the camera sees. Okay? And that's something, you know, we have to develop in our applications. Then we do the projection, which takes care of what the camera does, how it distorts things depending on the lens, and also on the size of the camera. You know, how much can that camera see? How big is the film plane? That's the projection transformation, and it involves a process called clipping. And clipping says, look, everything that's outside of this volume that the camera can see, I'm going to throw away. I'm not going to process any further. And anything perhaps behind me, I'm not going to process any further. And in computer graphics, there's always going to be a front and a back. It's going to say, I only want to see things between some distance in front of my eye or where my eye is up to some other distance, not out to infinity. And that defines a volume. In orthographic viewing, it's a parallelepiped. In perspective viewing, it's called a frustum, which is a cutoff pyramid. And that's all done by the projection transformation, which in when we don't have a fixed function pipeline, we have to define that function ourselves, but we can give you the matrix for doing that. These are all matrix transformations. Finally, we have to do something, and the clip coordinate space is normalized. So that's going to be normalized essentially to a unit, actually not a unit cube, to a cube that's centered at the origin with sides going from 1, 1, 1 diagonally down to -1, -1, -1, okay? With a W, actually it goes from W, W, W to minus W, minus W, minus W. But then we're going to go back from 4D to 2D to 3D by dividing out that W. That's called perspective division, and the W goes away. Okay, so OpenGL is going to do that part for you. You also then that results in a coordinate system called normalized device coordinates, which are very simple coordinates. Everything's been normalized, everything looks good, things have been clipped out. But then we have to decide where on the screen we're going to put things. We don't have to occupy the whole window that we've specified in GLUT for a particular image. We might want to divide it up into multiple parts. We might want to use one part for menus, or if we're doing a multi-view projection, we might want to have one part for a side view, one part for a top view, one part for an isometric. And so the viewport transformation brings us into 2D space in terms of pixels, but says what part of that screen do you really want to occupy? And those coordinates are called screen coordinates or window coordinates. So that's the sort of pipeline in terms of transformations that we go through. Now, the camera analogy is, we've actually, pretty much said this, that the camera analogy is basically saying that what we're doing is pretty much what the camera does, where the projection transformation is somewhat aligned to changing the lens on the camera. The viewing transformations are, how do we orient that camera? If you think about orienting the camera, placing a camera on a tripod, you have 6 degrees of freedom where you place it, and then you can rotate it in 3 independent ways. So that's essentially what the model view transformation does for you. And as we've said, the viewport says how big and what part of the screen you want to occupy. The modeling transformation takes the pieces that are predefined and brings them into your scene. Okay, now, these matrices are all going to be 4x4 homogeneous coordinate transformations. With the exception of the projection matrix, they're generally called affine transformations because they preserve lines. All of these, if you think about the normal operations you do, scaling, rotation, translation, even projection, a line always is a line. And these always preserve that property. So in computer graphics in general, that matrix has some structure to it, but it is a 4x4 matrix. And so what we do is we define these transformations by 4x4 matrices. We start with the representation of a vertex as a 4-element array in homogeneous coordinates, and we multiply it by a succession of matrices that are essentially these transformations. So if we are in our own code, we're writing a model, generally a model view transformation, a projection transformation, and the rest of the stuff is done inside of OpenGL by your GPU. And so when Dave said a few minutes ago about shaders, that the shaders are going to be a little bit more complex. They're going to be more complex because they're going to carry out these matrix multiplications for us. So it's going to be one line. It's going to be, say, I'm going to pass in as a uniform variable, I'm going to pass in a model view matrix that I've computed, I'm going to pass in a projection matrix that describes my camera, and then I'm going to carry out the multiplication on every vertex in the GPU because I've passed them in as uniform variables. Let's go back here. Okay, so we have to say, well, how do we set that stuff up? And everything, as I said, outside of this frustum for perspective viewing is going to be clipped out. Okay, well, how we do that is a couple of things to note and to be careful of. In that, in OpenGL, There's an issue, this one always gets people confused, and it gets hard to explain, but let me put it this way, is that we haven't yet addressed the problem of right-handed and left-handed coordinate systems. That, right-handed coordinate system, if you take your right hand and you take your first 3 fingers, that your thumb, if your thumb is in the X direction and your index finger is the Y direction, the middle finger gives you the Z direction. And so if you have the typical thing that if you want X going to the right and Y going up, positive X would be, positive Z would be going into the plane, right? Is that right? No, I'm off. No, I must be off. No, it's coming out, right. The positive Z is coming out of the plane. And so negative Z's are going into the plane. Now, the rule in OpenGL is sort of twofold. One is it doesn't enforce right-handedness on you, but you have to be careful because generally most things we do are right-handed. The one place it starts coming up is when you start defining viewing. And so generally we tend to stick with right-handedness, and the default camera is pointing in the negative, it's located at the origin and is pointing down the negative Z-axis. So the problem now is if you have a bunch of objects and they're kind of all over the place with respect to positive and negative Z's, you want to either move the objects away or pull the camera back from them. Okay? Now these are equivalent operations, but if you don't think of which one is moving and which one is fixed, and sort of in your own mind decide how you want to think about this, you can get yourself in serious trouble because your camera is going to be pointing in the wrong direction. So I think the most convenient way, usually in the OpenGL literature, is to regard the camera as being fixed and the objects as being movable. Now, this is counter to how physicists look at things. I mean, historically, the art world looked at the camera or the viewer as being primary, and you picked up an object and you oriented that object so you saw what you wanted to see, which face of it you wanted to look at. But from a physics point of view, it's the objects that exist in certain locations, and it's the viewer that moves around. So OpenGL sort of got caught in the middle. And so the thing to be aware of is this basic position that OpenGL regards the camera at the origin pointing in the negative Z direction. Now, if you want to move your camera or your objects, you can pick which one you do. I'm trying to keep with the fact that the camera is fixed, or use the view that the camera is fixed, and I'm going to move those objects into the negative Z plane to get them in front of the camera. Okay? You want to look at it the other way, that's okay. But here's the other point I think you have to do. In the OpenGL, standard OpenGL functions, talking about cameras, and this was an issue in the fixed function pipeline and in deriving these matrices, that distances were measured from the camera to the object, not the other way around. So when you talked about where the near viewing plane was and where the far viewing plane was, even though they're in this negative half space, they're a positive distance from the camera. And always the near plane is always closer to you than the far plane. Okay? Now, as I said, you're free to do it any other way because the fixed function pipeline did it. But I think that's the standard way in all the graphics literature, is to think about the distance from the camera to the near plane and to the far plane. And generally those don't have to be, but generally those are positive distances. Okay, and if you do it that way, and then you specify your views, your orthographic view and your perspective view, by right how far from the camera you go to the right before you clip things out. L is how far you go to the left before you clip things out. Top and far and near are the distances to the far and near planes. Top and bottom are the distances from the camera to below the camera and above the camera, which again could be negative. You just want top higher than bottom. These are the standard projection matrices, which in fixed function OpenGL were built in. But in present OpenGL, my advice is use these. You know, you can do your own, but these are correct, and they will generally give you what you would expect to see. Okay, now one of the things that you can do about positioning the camera is you can think of, okay, I want to position this camera with respect to the objects to see what I want. Well, you can do a whole bunch of rotations and translations to get the camera where you want. You know, so for example, if I have an object and I want to get away from it, I'm just going to translate the camera maybe in the Z direction to get away from it. But if I want to see the other side, there's going to be a rotation of, say, 90 degrees if I want to see around from the x-axis instead of looking from the z-axis. Well, you know, you start doing more complex things. What if I want an isometric view looking at it from up here someplace? So there's a function that was built into the GL utility library that was very helpful, and Dave and I have put it in our little package, which is called a look at function, which says rather than forcing people to compute these things all the time, let's do it in terms of a more useful from a user perspective function and say, I'm going to give you the information you need. I'm going to tell you, I want to know what it looks like from an eye position, where I would put the viewer in the world space. I want to know what it looks like for a viewer at this point, and that viewer is looking at a certain point. That's called the at point. So you have the eye point and the at point, which define a direction that you're looking. Now, there's a degree of freedom missing because you can still rotate around that line. You know, think about, you know, the picture of an airplane spinning to the ground, and you're taking a picture from the nose of that airplane. It's spinning. You're going along a certain direction. So you also are going to specify an up direction. So the three vectors that go in here are the I, the at, and the up direction. So generally the up direction, if you want it to be the normal up direction, you define it as 0, 1, 0. Okay, so we put that function in there, and effectively that's the standard model view matrix. If you want to know how things look like from the camera, this would be your model view matrix, and you pass it into the shader. Okay, here it is in terms, if you ever wanted to derive it, here's its derivation in terms of the vectors. You can, you know, do this little exercise yourself, or believe us. Okay, now what about the other more basic operations? Well, the three most basic ones are rotation, translation, scaling, and you can actually show that you can get an arbitrary affine transformation by combining these in some order. So what translation does is simply move without reorienting the object. You know, there's a lot of ways to get one point to another point, but only one way if you want the whole object to essentially move without any reorientation or rescaling. Now, this is the one that if you go through the mathematics, which we won't do here, is the reason that you need homogeneous coordinates. You cannot do this as a matrix vector multiplication in 3D. But if you go to 4D, you can do it in 4 dimensions, and therefore everything becomes a pipeline instead of having two different kinds of operations. So this is the simplest in some sense, but the one that's different from the others. So this matrix will, and if you look at what it does, if you multiply it by, say, XYZ1, it says that the X is the old X plus TX. The Y is the old Y plus TY. And the new Z is the old Y plus TZ, and it doesn't do anything to the W component. Okay, but that's what you want from a translation. Scaling, you want to allow for independent scaling in any of the three directions. Not uniform scaling, all the scale constants would be the same. So if S is bigger than, any of the S's is bigger than 1, it expands in that direction. If S is less than 1, between 0 and 1, it contracts. If S is negative, it scales and it flips. So it's also a reflection matrix. It flips it about that axis. Now, rotation is, the general rotation you want is a rotation about an arbitrary axis or an arbitrary direction in space. But there's another factor that comes up, and actually comes up in scaling too. If you rotate something, there's always one point that doesn't move. And that's called the fixed point of the fixed point of the rotation. So what we're going to define is assume the fixed point is the origin, that's always going to stay the same. And if I want a different fixed point, I'll combine it with translations in order to get, the idea would be that if I want to rotate something and keep the fixed point up here somewhere, bring it down to the origin, rotate it there, and then put it back at the end. So I can always combine transformations to get what I want. So here's the simple transformations, where this is sort of the mathematics of doing a general rotation about an axis, rotating, let me come back here for a second, rotating theta degrees about that axis that you see. Which axis are we rotating about? Let's say it's the red one. You're rotating by theta degrees around an arbitrary axis. But what we're going to do in general is not do this, because generally you don't have, this one gets a little ugly. It's much easier to actually do simple rotations about x, y, and z and combine them to get this matrix that will do the arbitrary rotation. So what we see in this vertex shader, which is essentially the vertex shader that we're using that I just showed you the results of, what we're going to do is we're going to rotate separately about x, y, and z by giving you an angle theta that we want to rotate. So actually what this does, this really shows some of what GLSL will do for you. Note that angles is a vec3. So you're passing in actually 3 angles. One is going to be the rotation I want about the x-axis, one is going to be what I want about the y-axis, and one is going to be what I want about the z-axis. Okay, so vec3 that. Then when I do cosine of those angles, these functions are all overloaded. So what that's producing is a vec3 of the cosine of three angles into that vector, and the same thing for the sines. Okay, so it's a very, it's all these functions are overloaded in GLSL. So now I can take the individual components from those rotations, Cx, Cy, and Cz for the cosines, Sx, Xy, and Sz, and define in the shader 3 rotation matrices about x, y, and z. And notice what they do. You can, do the mathematics yourself to prove this to yourself. But notice there that a rotation about the x-axis doesn't change the x values. A rotation about the y-axis doesn't change the y values. So all of these primitive 3D rotations are actually 2D rotations, but about in 3 different directions. But when I put them together, I can get an arbitrary rotation in 3 dimensions with a fixed point of the origin. So if you do that, look at what happens at the end here. We pass in a color, and all we're doing, this is exactly the program I showed you. We're passing the color through to the rasterizer, so it's interpolated, which is why you saw those colors changing across the face, but the position is being changed by the product of those 3 matrices. Doing an X rotation, followed by a Y rotation, followed by a Z rotation on the position that came in as an attribute, and that's going out as GL_position. Okay? So now, with just that little change, this has become a much more interesting and powerful project, and the thetas are being sent in from the application. Okay, so I can send them in as uniforms. What I'm doing in this application is, the one I showed you, is I increase one of them each loop. Whichever one you clicked on keeps incrementing until you click on another one of the buttons, and then it increments a different one. Okay, but that's essentially that program. Here's, sending it over. So there's the uniform that's sending it over. It's just saying I want to send over theta, which is, back up on higher. We identified that with the theta variable in the shader, and I send it over, and then I draw arrays. So each time I do it, I send over a new array of 3 thetas, and then I do draw arrays. So essentially no information is being sent over except these 3 thetas. Now you compare that to what think of this, what if this object wasn't a cube? What if it was an object that had thousands and thousands of vertices in it? This program would be essentially the same. all I would have to do for every iteration is send over the 3 thetas. This is where the power of the GPU comes in. In an older style thing, what you would be doing is computing, and this is effectively what would happen if you were using the old fixed function pipeline, which had rotation matrices built in. What you would be doing is you would be doing the rotation in the application, not doing the rotation in the shader. And you'd be sending all the data over. So if you had a more complex object than this square, than this cube, it would just slow you down tremendously. So this is really, as simple as it is, it's showing you the power of doing things with shader-based applications and not doing things in your application, doing it in the shader.
So this section's about lighting. In fact, the entire section is about computing a color. So you see a lot of math. I'll explain a bunch of concepts. And at the end of it, all it does is give you a new RGB to apply to a fragment. But without lighting, your scene really isn't very realistic. So for example, you see on the right-hand side of the slide there, in one case you have a circle and a triangle. On the bottom, well, it's exactly the same stuff, but because of the highlights, you get to see all the features that go along with it, right? You can tell it's a shiny sphere, and it's a shiny cone. You can even predict which direction the lighting comes. There's a lot of information that's conveyed in lighting, and it gives scenes a lot of realism. Now, since this is an introductory course, we're going to talk about a very simple lighting model that can be used for computing these things. You can do it in the vertex shader, and you'll get reasonable results. In fact, the ones that are there are actually done using a vertex shader, but there's a whole lot of geometry in the sphere and the cone to give that kind of smooth aspect. Or you can do the work in the fragment shader and you get high quality results. In one case it may be faster, in the other case you may get higher quality, but this allows you to have a little metric for figuring out which mode you want to move faster with. So computing lighting in OpenGL, a very simple model for doing this is something called the modified Phong model. And it has a whole bunch of components that go with it that I'll go through here in the next couple of slides. But effectively, you have an extra vector called a normal vector, which describes the surface you've got, a bunch of material properties that describe the object you're on. So is it shiny? Is it dull? Is it red? Is it blue? Characteristics like that. There's a bunch of other information that can go into the model. The viewer's position, so if you think about looking at a shiny car out in the sun, and you move your hand around, right, the sun's spot will move around on it. Well, how do we actually build that into the model? And we'll discuss some of those other pieces. In this particular case, this is called the Phong lighting model because the gentleman Phong figured out basically how to build a model that gave realistic looking results. There are modes. This is what's called Phong lighting because it's computed in the vertex. If you do it per pixel, which means you take all these lighting computations I'll show you and move them into the fragment shader. It's what's called Phong shading. It's exactly the same computation, it just happens to be done in a different place, and you get a little bit more useful, better quality results. Here's the important point. If you do the computation in the vertex shader, what you wind up interpolating is colors, and it turns out that's not physically accurate. It's not exactly the way you want. If you do it in the fragment shader, you actually wind up interpolating the lighting normal, fine, whatever, we'll get there in a moment, but it gives you better quality results. However, once again, it's a speed comparison of which one's better. I'll do this demo, or I'll do this part talking about having it in the vertex shader, but like I said, you can lift the code and drop it directly into a fragment shader and increase the great look of things at very little cost. So this model relies on a couple of different things. The first of which is called a vertex normal. So in this diagram you get to see here, on the blue background, the little purple sphere represents a vertex in space, and the normal is a unit vector pointing the direction, basically that's the curvature of the surface. So this is a sphere, and it's just perpendicular, right? If you had a rock or something, your normals might be kind of random across the surface. For something that's nice and smooth, you'll generally have a nice gradient for your normal as it goes across. But the long and short is, this is just a little vector that emanates from a vertex that tells you what direction the surface is changing in. Now, we use that computation use that vector in computations, taking in the position of the light and some other pieces to determine how, what contribution the light actually does to the surface. For example, if the normal's pointing, if you think about, like, say, a basketball with a light shining on it, if the normal's pointing away from the light, or more specifically in the same direction as the light beams are coming towards it, it's actually in the dark side. So we can use some of these mathematics to figure out what we're looking at. I'll explain those more as we get there. But this is an additional vertex attribute that we're going to see appear in all of our vertex shaders. Now, the model that Fong put together had 5 components inside of it. They're listed here, and the most important is the diffuse color. Diffuse is basically, when you look at anything in the physical world, the first color you recognize is the diffuse color. So these chairs are blue. The carpet, well, it's kind of a bluish hue. If you look at the wall over there, it's gray. The first color you see is diffuse, and it's arguably the most important that goes on there. Everything else are illumination characteristics. So the model says, okay, that's the base object. What are the other things that go into this? Well, quite often, if an object is shiny, it'll have a highlight on it. If you look at all the chairs in the room, right, you'll see reflections of the lights back there. We'd call those specular highlights. So we are able to adjust the color of what those highlights are. In the real world, right, the reflection or the highlight you see is a combination of the color of the light coming in and its interactions with the material it's reflecting off of. Computer graphics, we've got none of that, right? We're drawing a triangle, so we make up a lot of stuff on the fly. We just kind of go, yeah, the highlight looks like it should be white. Quite often, white's a really good choice, and we'll use that quite often. Ambient is the color of an object when there's no direct light on it. So if you have your feet underneath the chair, there's light that's bouncing all around the room, but not directly shining on your feet, yet you can still see your feet. That's the ambient light. So that would be the color of an object inside of a dark room with no direct light shining on it. You can add that into the model. Emission, basically if the object glows, so if you're modeling fireflies that exist on the east coast of the US, right, they got a little tail end that glows, you might say, hey, that part's emitting light. Important point, rasterization, the technique that OpenGL uses, processes every object individually. Every triangle is rendered in isolation. So I don't know how many of you come from the east coast of the US, but fireflies, right, if you catch them, hold them in your hand, the light will illuminate part of your hand. If we're doing this in OpenGL with this model, we actually don't get that secondary effect. Each primitive doesn't know about any of the others. So the lighting model in this one is quite primitive. Now, there's a lot of techniques that are happening to enhance the lighting characteristics that are outside of the scope of this course. There are light maps that go along with it and reflection computations, cube maps, and a lot of other things to give better lighting results. This is just to kind of get you pointed in the right direction, give you a foundation for exploring more pieces that go along with it. And the last part is shininess. Shininess in this model is just a representation of the smoothness of the surface. For example, a billiard ball would be very smooth. A rock would have a shininess close to 0 because, well, they don't really reflect light and they don't concentrate highlights. So that shininess is really a measure of how concentrated the highlights are. Now, in this model, you can actually have different material properties for the front and back of an object. And there's an extra variable that is available in GLSL that will tell you, are you looking at the front of a polygon or the back of the polygon? The rasterizer has some magic, and we'll just leave it at that, for determining which side you're looking at. It's based on the order that you pass vertices into it. But it allows you to go, hey, I'm looking at the front side of an object or the back side, and inside of your shader you can simply have an if that says, if I'm front side, use these materials, if I'm back side, use some other ones. So let's look at how we might actually implement this in the shader. Now, you'll see a lot of variables that are introduced inside of here. One, we have our vertex position and our vertex normal. So those are attributes that come along with every vertex that comes in. And we have our output color. Once again, all this computation, all the math you'll see is nothing more than figuring out the color, a single color for each vertex. Now, the next parts here are a combination of a couple of different things. We have some global variables that represent our material properties. So we have an ambient product, a diffuse product, and a specular product. We'll see those are actually computed in the application. That the formula for this is quite large. It's discussed in the notes. But basically, these are just a couple of optimizations of taking constant values together. What's important is ambient gives you the ambient contribution, diffuse does the diffuse contribution, and specular does that. And you'll see how we apply that along with the geometry of the situation, where the vertex is located in the normal. We have a bunch of transformation matrices, our model view and projection like Ed just spoke about, the light position, and a variable for shininess. So the first part, we construct a number of vectors that supports lighting. Now, once again, this has little to do with OpenGL and a whole lot to do with computer graphics, so it might sound a little obtuse, but really this is a way to add realism. So one of the first things we do is compute the eye's position in what's called eye coordinates. Eye coordinate is that coordinate space where the camera is sitting at the origin looking down the minus z axis. And we compute that by multiplying the position by the model view matrix. And in this case, we really want it just to be a vector and not a point. So we lop off the w coordinate and make it a vec3. So now we have this position in space. Don't care where it is, because this is all vector math. Then we compute some other vectors. The L vector is the position from the light to the the point in space that we're illuminating. So if the light bulb's over there and the point's here, it's just the vector between those. The eye position is the E vector, which is basically where's the eye located. And you'll note here we just negate the position, and that's the vector from the origin, because that's where the eye is sitting at eye coordinates. That was on an important slide a while back, to out to the point. And so you take minus 0, 0, 0 minus that position. Well, that's where we get the minus pos. And then we normalize that. So we're working here completely with normalized vectors. And the last one's this magic vector called the half angle vector. Half angle's very intriguing because it's what allows you to kind of have the highlight move around on the surface. If, for example, if you stand in the sun and look at a highly polished car and move around, the highlight will move. It's actually the half angle vector that's doing all that kind of computation. So this is the cool part, right? There's a whole bunch of physics, a whole bunch of realistic world stuff that's boiled down to 4 vectors. Now, we do a couple of things. We take our input normal and transform it into eye coordinates so that we're working in the same space. So we do a little bit more math. Basically, if you take any value, your position, your normal, and multiply it by the model view matrix, it'll take and map it into eye coordinates. So now everybody's in the same space, and we can work with those. And once again, we just take the normal, trap it to a vec3 because it's a vector, and normalize that. Now, hang on to that alphabet soup because the next page discusses computing all the different components. So the first part we do is just compute the ambient contribution. Ambient's not a directional light. You can't trace ambient light back to a light source. As such, it's just a color that gets added in. So, most often ambient light is some dark shade of gray, maybe 0.1, 0.2, and so that's what we pass in there. The next element that we compute is called the diffuse component, right? The base color. So all these things that say ambient product, diffuse product, think of that as the color associated with that material characteristic. So our diffuse is the base color. In this one, we do a little bit of mathematics to determine effectively what the contribution of the light is on the part of the object that sees it. Imagine you're standing on a basketball looking at the light. So here I'm staring at the spotlight, right? All the light from there is coming onto the front of me. If I were a little guy on the back of me, I couldn't see the light because I'm kind of obscured here. I'm facing away from it. That factor KD is what computes that. We just use a simple dot product that looks at, if the light's there and the normal's there, the ratio of how much contribution that is simply the dot product between the two. So we compute that, except if it happens to go negative, which is when one vector is pointing one direction and another one's over 90 degrees opposite to it. In that case, it's negative. So we just clamp that to 0, saying, hey, that's on the back side of the object. We use that as a modulation factor to compute the diffuse component. The math is pretty simple. You take the dot product of L and N, and then see if that's greater than 0. Great, use that. If it's not, just set it to 0. Multiply that to get your diffuse color. Specularly, we do similar things. We use a different set of vectors here. In this case, we use the half angle vector dotted with the lighting normal. And then we take the result of that and raise it to the shininess. This is just the computational model that Mr. Fong made when he put all of this together. What's it do? Once again, it just computes the coefficient to determine how much contribution for that part of the object should be received from the lighting environment around it. And here we do a little bit of special stuff. If, once again, the light's position is on the opposite side of the object, basically on the back, you're not going to see highlights because the object's obscuring it. So in this case, we just set the color back to 0, or more specifically, black, which is a vec4 of those things. We do our magic with the position, right? Every vertex shader must have that. And compute our final color, which is the combination of the ambient part, the diffuse part, and the specular part. Exactly what the model said. Pull and multiply those in. This vertex shader doesn't include an emissive term, but if you wanted the object to pretend to be glowing, you just add some additional color inside of there. And this last part, color.a, all of these colors here include a fourth component called alpha. Alpha is used for something what Ed mentioned called alpha blending. Fortunately, it's something that's a little outside the scope of the class, but effectively it just allows you to combine 2 colors at a per pixel level. In this case, we don't want our object to be transparent, and that might have creeped in through some of our values from the material properties. So we just lock the alpha to its maximum value, that of 1. And so in this case, what we've done is done a whole lot of computation to generate a color, but based on a whole lot of parameters that we pass in that vary per vertex. Now, you could take this exact same code and drop it directly into a fragment shader and do almost the same operations, well, in fact, exactly the same operations, to compute the color per fragment, every pixel on the screen, and you'll get much finer results, but probably a little bit of a performance penalty because there's a whole lot more fragments on the screen than there are usually triangles that go along with it.
I have a whole bunch of examples here, and so depending at the end, I could show you exactly the example that Dave was showing you of the that if you do exactly the same computations fragment by fragment, you get a very smooth result. If you do it vertex by vertex, you get very nice colors that show the effect, but you can see the individual facets that make up the object. So at the end, I can run through a bunch of examples and show you all of these things we've been talking about. But let's go through a little bit about the things you can do with fragment shading, and just to give you an idea of what's possible. I mean, if you look at where the action is in terms of shader-based graphics, it's really in the fragment shader because you can do incredible things. So let me give you a couple of examples. One is per fragment lighting, which we've just been talking about, do exactly the same computations in the fragment shader. So what the vertex shader does is just pass the stuff along to get interpolated. So if you give it a normal that you computed in your application, you send those normals over. The normals then go from the vertex shader out to the rasterizer, which then interpolates them over the little facet, and then allows for much better, smoother shading computations. Okay, so a couple of things that you can do in vertex shaders is one of the things you can do very easily is move things around, and I can show you a little example of that. You pass in a vertex and you can change its position. Now you can change it very simply, as we saw in the example a few minutes ago, just rotate it. But you can also do things like this. I can pass in a square mesh and then just have the Y component change in time. I pass in a time variable as a uniform, and then I have a wave I've created or a banner by just passing in this one parameter over and over again and letting the positions change inside the vertex shader. Another thing you can do very easily in a vertex shader is something we call cartoon shading, which turns out was in the fixed function pipeline was almost impossible to do. At least in any kind of reasonable speed. The idea here is, suppose, what is characterized as a cartoon, it's generally fewer colors. So suppose I was having some curved object like a sphere, and I wanted to use only 2 colors to display it, but I wanted to have lighting matter. So if the light source mattered, where I'd see one color versus where I'd see the other would change in time. Well, that's a trivial change to a vertex shader, which just simply looks for that change of where the light is and then colors it in color A or color B, but it's something that's almost impossible to do well and efficiently if you do it in the application. So these kind of things work very, very well. But when we get down to the fragment shader, that's where the action really happens. So one example was this example that we can do per fragment lighting much, much smoother and nicer. Second is that we'll use samplers, and that'll allow us to do texture mapping, which we're going to talk about in a minute. And a third variant, which is called bump mapping, which is a variant of texture mapping, which allows us to make it look like the surface has a tremendous amount of detail in it and changes with the light source, when in fact the surface is very, very simple. And we get that by playing with the normal in the shader. So if in the fragment shader, I can vary that normal a little bit, what does the normal do? It really gives me the local surface orientation. The local surface orientation affects the color I see when lighting is turned on. So now if I'm going to move the normal a little bit, automatically in the fragment shader, this surface is going to look very, very complex. And again, it's something that we could not do if we didn't have programmable shaders available. So we'll see some examples of doing it. Here's a little example of a height field where you want to display a function, and suppose you have a function where the heights, the y values, are given as a function of x and z. You can discretize that into an array of values of y for every x and z and display it as a surface. Well, here's a very simple little program that generates that mesh. What it does is it takes 4 adjacent points, makes a little 2 triangles out of it, and makes, or in this example, makes just a line loop of four points, and now you can display it in time. This is the example I just mentioned, and I'll show you it on the screen a little bit later, where you now change the Y position by just sending in a time variable as a uniform, use the same model view matrix, the same projection matrix, and just let that position change sinusoidally. Now you're doing no work on your CPU. The CPU can be doing other things, and here's this surface which is shimmering around in a sinusoidal way. Here's an example, just one frame of that, and I'll show it to you moving. Okay. We can also do that very easily. You say, well, why is it done with lines? Why don't you do it with a surface? Well, that's trivial. We just change it back to two triangles instead of doing a line loop, and then turns out the code will be almost identical if you compare this. You're doing the model view matrix, you're doing the sinusoidal thing, but now we're adding lighting. We're going back and just adding the lighting model that Dave just talked about to this. So the positions are changing, but the lighting model's the same. And you have the diffuse, specular, and I'm only doing diffuse and specular here, and we compute the color components, and we get this. It's again, all of these are incremental little bitty changes that make for some very, very interesting graphics.
Okay, I'm talking about texture mapping. Texture mapping has a gazillion different options and things. Here's the fundamental object. A texture map is nothing more than having basically a picture and pulling a color out of it. Just keep that in mind as we go through all of this. The object of texture mapping is to take an image and wrap it around some geometry. So in this particular case, our geometry is that trapezoid shown up there in white. And what we're doing is taking this image, this forest scene, I assume that's from Ed's house, and mapping it onto that object. Now, there's a whole bunch of things that occur on this, and you actually have complete control over how the colors are taken out of this image and applied to that object. And the interesting thing is, this just manifests itself as source code in a fragment shader. So the vertex shader controls the positioning of the object, and to some respect, controlling how the coordinate spaces that work along with texture mapping go off there. I'll talk much more about that in just a wee bit. But the fragment shader is the one that basically goes and gets a color from that picture and applies it to each fragment inside of there. So texture mapping has an awful lot of capabilities. It is the fundamental technique in modern graphics, as Ed mentioned. Most of the exciting things are happening in fragment shaders, and this is a lot of it. But the fundamental idea is you just have a table of information and you look up in that table some stuff that you use in a computation in a fragment shader. I'll tell you all the details about it as we go through. So, texture mapping is fundamentally the union of geometric primitives and imagery primitives, blocks of pixels. Now, when you surf the web, when you go to your camera, right, what you're actually pulling out are image files, not a texture map. OpenGL makes a big difference about that. For OpenGL, a texture map is merely an array of pixels with no other information about it. An image, on the other hand, for example, say a JPEG, has a width and a height and a color space, and you have compressed pixels inside of there that represent all the information for being able to display that image. And then there's a library that will read that file, uncompress all those pixels, and either draw them to the screen or whatever. OpenGL wants kind of that final thing where all of that information has been used to decompress the pixels from the image into an array. OpenGL wants that array. So we'll talk about pixel rectangles in here, and it can be stored in an image file, but there has to be a conversion from that into just a simple collection of RGB values or RGBA values. So we'll actually put the pixels and run them through a pixel pipeline. There's some ways for unpacking data in memory so that it's convenient. You don't have to do lots of mem copies and whatnot. But effectively, OpenGL will hang on to those, and then the rasterizer will provide you all the information required to figure out how to access those pixels along with your incoming geometry, pass that into the fragment shader, and once again, you're just computing color. The process is pretty straightforward. Now, for texture mapping, there are three fundamental steps that you go through, and this is mostly to get OpenGL to remember your texture data. It turns out in the fragment shader, this will look blindingly easy. It's very similar to what we had to do, all the plumbing and all the setup for vertices, and in the vertex shader, you have a V position and you just manipulate it and go. The same thing will occur in a fragment shader, but before we get there, we have to give the data to OpenGL, And OpenGL being very flexible, accepting all sorts of data in all formats and different memory strides, there's some complexity, but we'll discuss those. So the first part is you actually have to give the texture image to OpenGL. You have to specify that. There's one call that does it, and it has 11 parameters. We'll discuss what they do and how they put together. The second part is you need to apply texture coordinates to vertices. So once again, a vertex we've labeled as a little package of information stuck in space, and that information is encoded in attributes. For lighting, we discussed, oh, hey, we can have a lighting normal. Other places we've said we can have a color. Another common attribute that you'll put with a vertex is a texture coordinate, or more specifically, maybe even multiple texture coordinates. There's no limit to the number of these you can do. Okay, there is a limit. It's like 1K. You can have 1,000 texture maps available and usable at the same time. But effectively, you know, you're being extraordinarily creative at that time, and your program will run extraordinarily slow. But anyways, that's a minor point. We need to assign the texture coordinates to vertices because the rasterizer is going to take care of interpolating those between the vertices, just like it did for colors and lighting normals and all the other attributes we've talked about. There's one other part that we need to do, which is specifying some additional texture parameters. I'll just lightly touch on that. Right, an image has a fixed resolution. And you know, you took it with the camera, it's 12 megabytes, and it's 1920 by 1280, whatever the size is. And a piece of geometry, a triangle, is under the control of many matrices in your system, right? So your projection matrix, your model view matrix will control how a triangle that has a size in world coordinates, whatever they might be, but how it gets mapped to the screen. And that transformation, like Ed talked about earlier, might take that triangle and map it to, say, maybe 10 pixels on a side, or it might map it to 1,000 pixels on a side. There's a whole lot more pixels, but the resolution of the image that you want to paste on top of it hasn't changed. And so there are parameters to help OpenGL know what to do in those situations. You know, if you have a primitive that's much larger than the image, what do I do in that case? And the opposite case, if I have an image that's much larger than the primitive I'm mapping it on, what do we do in those cases? And we'll talk a little about those later. But fundamentally, there are only 3 steps. So, like so many things in OpenGL, textures are stored in a texture object. We saw vertex buffer objects, vertex array objects. The code, you change the last word. It's glgen, in this case textures, that will make you an array of texture objects. So you call this in your init function, you make a bunch of them, and then we start packing data into them. Everyone good with that part? Because that's easy. Now, just like you've seen before, OpenGL is very keen on binding things. So once again, we can bind a texture. And that takes one of those objects you just allocated and opens it up so we can start chucking data into it. And the data we'll chuck in there is our texture image. Now, just like vertex buffer objects and vertex array objects, you wind up switching between textures quite a bit. And to switch between a texture, use the glbind texture function. You'll call it once initially when you set the texture up to be able to load data into it. And then you call glbind texture a second time when you actually want to tell OpenGL that this is the texture it should be using inside of there. So you'll see a lot of our rendering loop. You remember I said, hey, it always begins with glclear, it ends with swap buffers, and then we draw arrays in there. And then Ed showed an example where he updated a uniform. We might wind up binding some extra textures inside of there too to get those updated inside the OpenGL pipeline. So this is very similar to the multiple vertex array object part. You'll wind up binding the data that you need to do to draw the object. And in this case, it's just this simple call. The weird one, people are kind of unsure because you wind up calling this twice, once to update it, once to use it. Turns out it's exactly the same for vertices. We just didn't call it out quite as much. Now, this is one of the calls to load texture data into OpenGL. And this is kind of the Swiss Army knife function. This particular one loads a 2-dimensional texture. And so it'll have an X direction of pixels and a Y direction of pixels. I bring this up because OpenGL supports many different types of textures. It supports 3-dimensional textures where there's a width, height, and a stack of images as a depth. So if any of you need to do volume rendering, as you might do in a medical application, or maybe for atmospheric effects, you want kind of a realistic fire or kind of a fog that covers your scene, you might do 3-dimensional texturing to kind of get that effect. It's for volumetric aspects. 2-dimensional, of course, is just for taking a 2D image and splatting it on stuff. But that said, there are different 2-dimensional images that might be used. Another one, which is a little outside the scope of the course as well, is called cube mapping. And cube mapping is what you might use to set up an environment. So if any of you are gamers and heard the term skybox, a skybox is just a real cube map that they used for putting lighting effects and reflections and other things inside of a scene. You kind of bake in your environment, and that gets projected on your objects. But there are a family of functions, GL text image, various things, 2D, 3D. There used to be a 1D. and you can get that in the compatibility one. And for those of you who want to do like false coloring of an image, blue for cold, red for hot, one-dimensional texturing is very handy for that. There are a whole lot of options to this. The long and short of it is it tells OpenGL what kind of texture it is. It's 2D texture or a face of a cube map in this case. Something called a level, and we'll touch on this a little bit more, but there's a technique called MIP mapping. We won't be able to go into it in great depth here, but it's a filtering technique to give you better results when your texture is bigger than the object that it's on. So if you imagine having a basketball, when it's close to you, you get full resolution of the texture. When the basketball is farther away from you, it becomes very much smaller, but you still have the same resolution texture. The results don't look good in this. MIP mapping is a technique to make that look better. Level adjusts that. Components, width, height, border, format, and type basically give a description of both the texture in memory. Effectively, in your C program, you'll malloc some memory, store the colors inside of that. That's what goes in texels. Format and type describe what type of memory you used. Are they unsigned bytes? Are they floating point numbers? And type is it a red, green, blue pixel or RGBA? How do I actually decode the data that's off this pointer to know how to find a pixel's worth of information inside of it? Width and height tell me the resolution of the image. Border is a leftover part. Remember, this API is 20 years old. This is one of the original functions. And way back then, we used to be able to have a 1-pixel border around a texture. Unfortunately, that worked kind of like lead balloons, never worked the way people wanted. And eventually they said, right, we're just chopping all that out of the API. So that value is always set to 0. Nowadays, it's just like, we don't have texture borders, but we didn't make a new function call. So effectively, it's ignored. The components part basically says, internal to my texture, so when OpenGL, when you're storing this, please store this in a particular format. Now, quite often, right, if you have a camera, you'll pull down an RGB image, right? But maybe if you're using an art package like Photoshop or something, you might include transparency inside of it. That'll be an RGBA image. OpenGL has enough skills inside of it, so maybe you want a grayscale image. So you have a picture you want, and you want it automatically converted to a grayscale image. OpenGL knows how to do that in processing this call. So components here kind of says, what's the internal storage format for my image? If you just put GL_RGB in there, life will usually be pretty good for you. There's a lot of options. There's something on the order of about 64 different ways of specifying that parameter, but that one will do you in most cases. So that was a quick run through of how you specify the texture and get the data into OpenGL. Really, it comes down to just that one call and adjusting the parameters correctly and getting the data. The next part is the really important part, which are called texture coordinates. So the first thing you have to understand is what texture space is, right? We know what 3D space is because that's where all of our vertices live, right? You pick an origin, you define an x-axis, a y-axis, and z-axis, hopefully perpendicular, and then you measure distances from that and you label those as your vertices in world space. Texture space, particularly for two-dimensional texturing, defines a unit square that goes from 0, 0 to 1, 1 in 2 texture directions. The S direction is the horizontal one. In real-world space, we'd call it X, but just to keep us either more confused or less confused, we call it S here. And the vertical direction, which would be Y, we call T. So a texture coordinate is merely just an ST pair that you specify in 0 to 1, and then when you attach that to a vertex, well, it grabs the color at that point and pulls it over and applies it to the object. The rasterizer will interpolate your texture coordinates, and then each texture coordinate for each fragment will be looked up in the texture map, so in this texture space, and be applied to your geometric primitive. So in this example, you can see we kind of pull the center section where the 3 colors meet and map it onto a primitive. Once again, this is just looking values up in a table. We have a 2-dimensional index. We go out and get a color that goes along with it. However, I glossed over one small thing. Texture coordinates are only defined between 0 and 1. So the question becomes, what happens if my texture coordinate is outside the range 0 to 1? Well, that's some of those parameters that we don't have a slide on it, but that specify what we should do. If they're outside 0 to 1, we have some options. We could clamp them to this space. So for example, if you have an image and you're placing it on a billboard and you want it just like to have, well, if you had texture borders, which seemed like a good idea at the time, but you like basically want the picture centered in a polygon, you can clamp your texture values to 0 and 1 and center it in the middle, even though your texture coordinates might go from -100 to +100. That will put the image right in the middle, kind of small. If you went from -3 to +3, it'd make the image 30 times bigger, but still keep it right in the middle. Now, You could also do what's called wrap mode, which chops off the integer part and allows you to circulate through in your texture direction. So this allows you a repeating pattern. So you can take your texture and repeat it. So for example, if you look at this, there's some tiles up on the wall here in the conference center. Sorry for the people watching on YouTube, but there's a pattern that repeats across there. We'd actually grab one instance of that and just go, oh, it repeats 40 times across this direction and 12 up. And you set your texture coordinates to be 0 and 40 and 0 and 12, and you get this repeating pattern. So that's part of what's called a texture sampler, and I'll touch more on it in a bit. But that's the fundamental idea of texture coordinates. It's another space. You need to figure out what to do with the values between 0 and 1, and when they're outside, you need to tell how the GL should interpret values outside that space. So that's kind of part 2. Texture coordinates, right, they attach with a vertex. Now we're to the part where we actually do all the magic. We ask OpenGL, for this texture coordinate, return the color back, and we do that with a single function call inside a fragment shader. So here's an example where we take and we're kind of doing some lighting computations, but we've taken and baked a texture of the base color of an object. So something like the tile in the wall here where there's a pattern on it, and stored that away. The texture function, well, here it is, that we see here, right, takes and looks up in this texture at this particular texture coordinate, and all it does is return back a color. In this case, an RGBA color. We only want RGB, so we chop that off and do some other bits of work. But this is what does your table lookup. Now let me talk about some of the things that you're seeing inside of here real quick. Texture, obvious function name, it basically does the texture lookup. This, you'll note, is what's called a sampler. And a sampler is a handle to a texture map that OpenGL is managing for you. So you remember we generated a texture object, we bound it, we loaded it full of data. That texture object ID is the exact value here of this texture, or that's the value that goes in here. It's the index of that texture object you created. So what you pass into GL bind texture, you make available as a uniform and pass the value in here. So in your application, you make that specification by looking up a uniform location and calling GL uniform with that value. And that gives us the OpenGL a way to associate the texture values along with the pixels that you provided in the texture. The second part here is your texture coordinate, and we'll touch more on this, but note this is an input value that comes into your fragment shader, in this case a vec4, and it basically will look up in this texture the color that's associated with that particular pixel. Now, once again, what happens based on these texture coordinates? They can be any numbers, but they're only valid between 0 and 1. It turns out there's some state that goes along with your sampler that controls what you do if the texture coordinates are outside that range, what we do if there's more texture and smaller number of pixels, this what's called minification or magnification. So there's a whole bunch of extra information that's stored in the sampler that's all encoded that this function takes into account when it pulls the texture back. But the long and short is, you call this one thing and you get a color back and you're able to move ahead and do computation with it. So here we go, and we're going to apply a texture map to the cube. So we're going to augment that original example that you'd seen by adding a couple of things in. So the first part we do is we add texture coordinates attributes to every vertex that's in here. So we had colors and positions. Now we just add in some texture coordinates. In this case, we're being very simple. Each face of the cube is just going to get the texture mapped on simply. So we're going to have 0, 0 be one corner of the cube, 1, 1 be the other, and then do the respective texture coordinates to map it directly on. So you can see for the first corner, vertex A, we give it 0, 0. For vertex B, we move 1 unit up out the S direction across the bottom. And as we do the other ones, we'll go to texture coordinate 1, 1 and back to 1, 0 for the 4 vertices. Then when we render that, the rasterizer will interpolate those texture coordinates. We'll call our texture function in the fragment shader, and everything's good. So here we do step number 2, where we specify all of the texture coordinates in our example. Now, here we go off and generate a texture. And this would be what's sometimes called a procedural texture. It's not from an image. We're actually using an algorithm to generate this. We could do the same kind of thing actually in a fragment shader, take and encode this in there. It turns out, in this case, it might actually be faster to do that, but the long and short is you'll hear the word texture mapping have a lot of different definitions. In OpenGL, when we talk about texture mapping, we're using an image, which we're building here, that we give to OpenGL. You'll often read about procedural texture mapping, which is generating some kind of texture-like appearance algorithmically inside of a fragment shader. Not what we're talking about here, but I'm just saying you could possibly do that. This just generates a checkerboard pattern. it's also good obfuscated code. You sit down and look like, hey, they're using an XOR, what's going on? But all this does is make a checker pattern that's basically either fully white or a combination of red and blue, purple, and alternating back and forth. Now, here's all the boilerplate for specifying an OpenGL texture condensed into one slide. We generate our textures, we bind the texture, and additionally, one thing we didn't mention before is we set the active texture. There can be multiple textures available simultaneously. I made mention of this. To access each one, you'd have just a whole bunch of sampler variables in your fragment shader, and every time you call texture on one of those, you'll get a color back for their respective coordinates. And you can have a whole lot of them. The way OpenGL sets those different things up, they call an active texture, of which there's a large number of them nowadays, by default at least 16. So you call active texture, and that basically sets up what's called a texture unit. Just think of it as one spot where you can load a texture in. And so if you want two textures, you set one active texture, do all the work there, then call GL active texture to the next one and do the same thing. So we bind our texture that we created above, we load it up, in this case, with the image we just generated, giving it unsigned bytes and RGB and all the other bits. And then we set up a bunch of what are called texture parameters. And these are the parts I mentioned where they describe how the texture function inside your fragment shader is going to work with a bunch of different characteristics. One, what happens if your texture coordinates are outside of the range 0 to 1. And that's what happens with the first call here. You see this GL texture wrap, and you get wrap S and wrap T. For each texture dimension, so if you're working with a 3D texture, there's actually a wrap R that gets associated here. And you can tell it what to do. In this case, we want it to repeat. There's a GL repeat function, which basically says repeat the texture coordinates along that direction, and you stamp out multiple copies. There's a clamp and about 6 other variants. You can clamp to a border, clamp to an edge, but this controls what happens if your texture coordinate is outside. Yes, you could hard code this into your shader by doing modulo operations and whatnot. It turns out that there's hardware that's been around for a very long time that's very fast in doing that. It's much better to do it here. There's another part that we go along with. This is the magnification and minification parts. Don't have much time to discuss it, unfortunately. But here we're basically saying, find the closest pixel in the image and just use that. There are about 6 different combinations that you can use for your minification and magnification filters, and it's a combination of speed versus quality. The highest quality one is something involving something called mipmaps. They're described a bit in the notes inside of here. And they use multiple images combined together that are built automatically by OpenGL to combine together to find a fragment color that gives you the best quality for that. Turns out it's a little slower because it's doing a lot more work. Nearest is actually quite a simple mechanism where it just goes out and finds the closest texture that goes along with it. In this case, we're keeping things quite simple, so we set those up. All of these parameters affect the sampler that's inside of your fragment shader. You don't know it inside the fragment shader, you just see a sampler variable and use it, but these kind of parameters control its operation. So here's the complete vertex shader that goes along with it, and the only additions here are we have a texture coordinate that's on the output side. We're feeding that into the rasterizer that's going to take it and interpolate. And here's where we receive the input. So we're going to map this value into that one, and lo and behold, there's the one copy through statement that says, take your texture coordinate and pass it through. Most modern GPUs, when they see a line that looks like this, don't do anything except set a pointer. The instructions are kind of mapped out, but you can't assume that's going to happen. So you always need to write this line inside of there. Once again, we set our position to go forward. And here's our fragment shader. Really, there's very little to it. Once again, we do our texture, and here's our sampler, which accumulates all that state we had, the minification, the wrap modes, all of that, and our texture coordinates, which here, yes, even though it looked like we just copied them across in the vertex shader, are automatically interpolated by the rasterizer. So they're automatically updated for every pixel in the primitive. And then the texture function does all the magic of finding the right color, combining the right images if you're using advanced filtering modes, all of that to give you the right color that goes back. And here we actually, I'm not sure what this, this is combining a vertex color that came in, that was in the fragment shader from before, or the vertex shader from before, with the value in the texture. This is what's called a modulation mode. We're modulating the texture color by the base color. You might do this for an illumination map. So a common example of this would be, if you look at the wall here, once again, apologies to people, but if you imagine the lighting aspects are captured in the texture map, where it's bright, you get to see the full features of the wall. Where it's dark, you get to see mostly dark colors and not the features. A texture map is a great way to represent a light cone in that way, and you modulate the base color of the object with the light that you have in the texture map, and you get these kind of nice effects. Used all the time in games. It's a really good technique. So The long and short of it is, though, there's a whole lot of setup for texture mapping, but when you manifest it, it's just one function call in here that returns a color back. And you can do a magnificent number of things using that kind of technology. And that, I believe, is our last slide. So that was a bit of a rushed part on texture mapping, apologies. But at this point, now we'll open up to Q&A, and let me just quickly toss up a set of resources. So there's the 8th edition of the OpenGL programming guide that just came out that discusses everything up to 4.3 entirely shader-based. There's Ed's book, Interactive Computer Graphics. I wrote the bad code inside of it, the Vec4 classes and whatever. That's in the 6th edition. It's going to be 7 soon. I guess that's a commercial advertisement. The OpenGL Super Bible is another really great book. The Red Book, the OpenGL programming guide is commonly called the Red Book. That's kind of the tome of everything OpenGL. We discuss every option, every parameter, how it all works, and those kind of things. It's the encyclopedic part, and it came in at about 1,200 pages this time. The OpenGL Super Bible is kind of an applied approach to this. If you have a particular problem to solve and want to see it cast in OpenGL, have a look in that book. That one actually is about 1,800 pages, but it contains reference pages for everything that's inside of there. A bunch of other things. The OpenGL Shading Language Guide actually is kind of obsoleted, but there was one of those. There's some books that were specific. They're slightly dated, but ones that talk about using OpenGL in the X Windows system, programming for the Mac, or even programming in embedded systems, the OpenGL ES 2.0 programming guide. And there's a bunch of other books coming out on WebGL programming. I think that one's just being released. So at the time we made the notes, it wasn't there. That talks about doing WebGL. I think we have one more slide, which is certainly talking about the OpenGL website. So if anything OpenGL you want to know, newest versions, read specifications, see examples, reference pages, go to the OpenGL.org website. There are also discussion forums there that a lot of the OpenGL experts haunt and will answer questions on. There's also the Kronos website, which talks about all the related APIs to OpenGL. Specifically, OpenGL ES is discussed there. Get specifications and some other parts. I think we have one more, which is our contact information. So we have Ed's email and our email address, my email address. I won't speak for Ed at the moment, but if you have any questions, you're welcome to send me an email. I'm really
Send them to me, it's okay.
Yeah, I'm really wretched at returning them, but I will eventually get them back to you. So feel free to do that, and just don't hold me accountable on response time. Ed's a bit better. He's got less things to do than I do. And in the course notes, we'll make them available at these 2 URLs. There's a PDF. The same thing was made available on the conference DVD. So with that, let Ed run a few.
Yeah, ask questions and I'll run some examples while you're doing that.
Anyone have any questions? Don't be bashful. I just stand up here and be recorded, so you know.
Hello. Hi. So one of the earlier examples, you had 3 rotation matrices being multiplied together in a vertex shader.
Yes.
Is that actually more efficient to do that like on a per vertex basis, or to compose matrices together and pass it in as a uniform?
In the particular case, it's usually more efficient from an implementation, OpenGL implementation side, to actually combine those together, right? I mean, it's simple math. Right. You've got 3 matrix multiplies that you could do combine together and just have 1 matrix multiplied per vertex. The way that fragment shader was written, you've got 3 matrix multiplies that happen, and the compiler doesn't have a way to actually optimize that. So this is certainly an application case where you can go, these values are all constant. Can I actually do that multiplication work in the application and specify it? Good catch. Yes, absolutely. That would be a great way to do it.
Thanks.
This is two textures multiplied together. Okay, this is an example of Dave was talking about texture units. You can actually have 2 samplers, and this is the checkerboard as 1 texture, and as a sinusoid as a 2nd texture, and they're multiplying together essentially in 1 line again in the shader by having set up 2 simple textures, and we just have 1 line that says texture 1 times texture 2 times the color that we passed in. So it's very good.
This the Timothy Leary pattern? I mean,
Yeah. Well, we'll move to something else. I could stop it.
Any other questions, please?
A question for the vertex shader. What's the big difference between using a uniform versus in there? An variable.
So an in variable, so the question is, what's basically the difference between uniform versus in? And the answer maps to all the different shading stages, but yours was specifically at the vertex. The in variables will be updated per vertex. So for example, if you have 3 vertices, each one having 5 attributes, your vertex shader would have 5 in variables, 1 for each attribute, and it would be executed 3 times, once for each vertex. Each implementation would have a different value in those values for each one of the different vertices. Uniform, on the other hand, would be constant across all 3 of those invocations. So, go ahead.
Yeah, oh, okay, but in a single pass, you can't change the in variable across, like if you're rendering one frame, you can't change the in variable as it goes from vertex to vertex?
Actually, it's changed for you automatically. The in variables represent your data that changes per vertex or per fragment. Now, just a little background real quick. The reason it's called uniform, a uniform variable is constant across a draw call. So that's the granularity that you can change them. You can set a uniform variable called draw, and in your shader, that uniform will remain constant across every processing part inside of there. Then you can change it and do it again. So uniform was kind of, think of a uniform color across an object. It's the same across all the draw calls. But the in variables are updated every time the shader is executed.
It's also, I don't know if we pointed it out, but uniforms apply to both the vertex and the fragment shader, so you can pass uniforms into either shader.
I think I covered that.
Did you? Okay. I wasn't paying attention.
Please, next question. This is fun.
So, OpenGL has undergone a lot of changes in the last 5 years, right? You've got 3 and now 4. What took it so long from 2 to 3? And the second question is, Valve, the makers of Half-Life and Counter-Strike and Dota 2 and all that, they've made a lot of progress in improving the speed of Linux drivers.
They have.
So what do you guys think about that?
Question B, I'll answer my question. So question B, first, which is basically the improvement of Linux drivers, that's fabulous. The real world of graphics drivers goes, when gaming exists on a platform, the drivers get better really quick. Gaming is an amazing system for doing real time and those kind of things. So until we had a lot of games on mobile devices, they weren't quite as good as they could have been. But you know, you start getting gamers in there, people playing the games, they want the right things. So Valve doing that is all goodness, and I thank them greatly for that. The other question about the evolution of OpenGL, first we'll start it by design by committee. It takes quite a lot of time to do that, but there was a real fundamental change that occurred at OpenGL version 3.0. The OpenGL evolves under the auspices of a community called the OpenGL Architecture Review Board. It's one of the working groups inside of Kronos. It's composed of the graphics API guys, so you've got NVIDIA in there, ATI in there, I sit in that committee, and a large number of other people. Forgive me for not mentioning all the companies that are there. When OpenGL 3.0 came out, they said, this OpenGL has taken a long time to evolve to this point. We need to do it better, so we're going to be schedule-driven as compared to feature-driven. Previous versions of OpenGL were updated based on when we had enough features there. One, graphics hardware is changing very rapidly nowadays. But secondly, they basically said, we have a 6-month window. We try to make releases at SIGGRAPH and the Game Developers Conference. So let's just start a train that goes, here are the features for this version. Sorry, too much coffee. And then the next version, and they just started revving them in that manner. So they changed their engineering practices, and actually you've seen a lot of benefit from that, I hope. Do you have any comments?
Well, I think there's another aspect. One is that even under OpenGL 2, there were lots of advances, but there were extensions, and it got really be a mess to work. But I think another sort of side of it is that there's been this incredibly renewed interest in OpenGL, where because of cell phones and Macs and a variety of other things on Linux, that OpenGL is now running on essentially everything. And I think I was at one SIGGRAPH, I don't know, sort of in that period before OpenGL 3, where at the OpenGL Birds of a Feather meeting, the basic mood was that OpenGL was dead, that DirectX had won and there wasn't going to be any OpenGL. And within 2 years, everything had changed. And I think it's because this proliferation of other platforms where OpenGL is either running natively or is the standard to run on. And so the interest is has just increased enormously. And that drives the kind of things that you start seeing in GPUs and we talk about.
May I make one more
Yes.
comment? So to align with what Ed said, we'll get to you in just a moment, but one of the major features that has kind of aligned this is mobile devices and OpenGL ES. Right, OpenGL ES 2.0 full shader-based thing. To give you some idea about this, last year 1.1 billion mobile GPUs were shipped. You contrast that with about 300 million desktop GPUs. There's definitely a phase shift happening in the industry of where the new graphics devices are what are in your pocket. They're all mobile, but they're just as featureful and they're not as powerful in terms of being able to do as many things as fast as what you can do in the desktop. But you can do full shader-based OpenGL ES 2.0 on pretty much every phone that has a color screen on the planet. That's amazingly powerful, and that really brought OpenGL back into a lot of relevance. So, the gentleman in the back, please.
Yeah, I have a texture mapping question specifically related to quadrilateral warp meshing. In the good old days, when you had a quadrilateral mesh and you used GL quads to index your textures, you had bilinear interpolation across the quad. And when you replace it with triangles, you get bilinear across a triangle, and you can certainly see the diagonals that you use to tessellate the quads. Any simple fix you could recommend?
Well, certainly, so are you using GL triangles or GL triangle strips or?
Triangles or triangle strips, it doesn't really matter.
Yeah, I mean, unfortunately, this is an interpolation error. You can, there's some advanced features inside of the shading language that we certainly haven't touched on in here. There's a huge amount of GLSL that we didn't have time to cover. There are a bunch of directives for handling out variables in GLSL. So specifically, in Fragment Shaders, you can control the location of sampling in other parts. You can do centroid, interpolated. I may have that slightly incorrect. I know centroid is one. The long and short is, right, a pixel is the granularity that you can apply a color to. Now, that's true, but most modern OpenGL architectures use a technique called multi-sampling, where they take a pixel and actually pretend it's multiple little pixels and render at different locations inside of there. The fragment shader, depending upon how that's actually employed, may be executed every one of those little fragments or some representative set of them, or maybe just once and the colors shared across all of these guys. It's a technique called multi-sampled anti-aliasing. The centroid and some of the other ones control the location of those things and may improve the quality of that. But at one level, it really is just the interpolation characteristics along the edge.
What about a geometry shader? Would it handle it?
You would still...
Because it has surrounding information.
Potentially, but you still have this edge of a triangle. So Ed's comment was, would a geometry shader, or for that for that matter, a tessellation shader, would that help this problem? No, because they're all still just rendering triangles, and you have an edge of pixels that go along that. So yes, it's a recognized problem. The fragment shader tries to help that with some of these advanced controlling of where the sampling actually occurs. So,
okay, thank you.
You're welcome. Sir.
Yeah, so if I have to write a very simple renderer for a mesh, 3D mesh, is there any performance implications if I write using fixed function APIs or writing my own shaders, even if they're very simple?
So, would you like me to hit that one?
Yeah, go ahead.
Sure. So I'm the Luddite in the OpenGL community, and they all know it, right? There's no problem with doing fixed function. The problem is if you call GL begin, GL end, there used to be a way to specify geometry in a really simple, fine-grained manner. If you use vertex array objects and vertex buffer objects, like Ed mentioned, and then use the fixed function for just getting your geometry up there, there really isn't a performance difference. Underneath the seams, a high-performance optimized shader will be put in place for you because that's the way the hardware works. The API just obscures that from you. So you can do those kind of things quite well, and Mr. Kilgard is kind of like, hey, whatever gets your job done. So he doesn't say the new stuff has to be better. That's a perfectly fine approach to it. The one thing I would steer you away, you'll get a big performance difference if you start using the what's called immediate mode fixed function, which is begin and vertex and those things. That's what I would stay away from.
Yes, thanks for the presentation, by the way.
Thank you very much.
I was going to share two things that were helpful to me. One is considering ins and outs. Their original name as varyings, as opposed to uniforms, kind of helped me, remember what they do. or the relationship of varyings to ins and outs. You know, that kind of change is interesting, and I would love to hear you guys talk a little bit about the change of nomenclature.
Oh, love to talk about that.
But also,
Is there beer involved?
not only because they increment as you drop through the vertex collection or whatever the primitive happens to be, but there's the automatic interpolation when you drop down into the fragment. So they're very useful in that respect, and the interpolators are kind of free work that you get in between vertices. And I thought I would just point that out for her sake. The other thing is, in your book list, I thought Mike Bailey's graphic shaders, particularly the second edition, is just really, it's a superb kind of introductory text, whereas the Orange book is like a comprehensive reference, if you know what I'm saying. That was it.
Well, yeah, let me.
You go ahead, please.
Yeah. Mike's book has some wonderful examples of shaders. I was just talking to him this morning, but I think his book assumes that you already know something about computer graphics. So it's sort of like we were talking about it being the second course that people would take. But the examples are wonderful. The Orange book, I'm not going to say anything on record about. But somehow I always had trouble though with the name varying variables. There was something about that name that really bothered a lot of people, and I was one of them.
So you're absolutely correct. I will apologize to Mike because his book is great, and he's a good friend of ours. Sorry, just a omission on our part. Varyings, excellent question. So the thing was, a while back when shaders were first done, attributes were called attributes. Varyings were called varyings because they varied across a primitive. And so your fragment, or your vertex shader used to have attributes going in and varyings going out, and then your fragment shader would have varyings coming in. That was all fine, well, and good when they were matched pair like that, but now we inserted geometry shaders, tessellation shaders inside of there, and they're like, wait. So we didn't have a way to connect these two things anymore, so they just wiped them out. And data flows in through in variables and out through out variables, and then we set ourselves up to be able to handle any kind of situation that's inside of there. As a matter of fact, I realized my version of the OpenGL 4.3 pipeline is slightly incorrect because we added compute shaders. I may not have mentioned them. I believe the box is up there. But that's yet an even additional shading stage that's available inside the pipeline. So, excellent question. Anybody else?
Extremely excited about WebGL. What are some of the big challenges in WebGL? There are a lot of benefits, and clearly one of the things is the built-in windowing system in the browser itself. But what are the big challenges? Yeah, that's pretty much my question.
What are the big challenges? So that's an excellent question. Just for the folks watching, the question is, what are the challenges with WebGL? Fundamentally, it's twofold. Nothing that's not well known to somebody who works in the web domain, which is browsers support varying levels of functionality. So indeed, WebGL is a very well specified API. The organization that put that together has received pretty good things from the web on how it's put together. They also claim like, oh, denial of service is capable in this. Okay, that's fine, different issue, but the API is put together very well. However, the API actually resides on top of a graphics driver, and their graphics drivers are a lot of cases where you get variations in support and functionality and basically performance and how all these things go. So a lot of the interesting underlying elements of WebGL are actually based on the driver conformance underneath, how they all conform to the specification and how well they work. There's a lot of emphasis in the OpenGL world to better buckle up the quality of all the drivers, to make the standard, people go, hey, if I'm going to render a triangle and it's texture map and it has a seam down the middle, everybody looks kind of the same when they do that, to make it a lot more visually consistent across the drivers. We're not quite there yet, but we're certainly working in that direction. So for WebGL, the benefits are, as you point out, no more windowing system, inputs already taken care of, an extraordinarily rich environment that's provided to you by the web browser to develop your application. The downside is you have to test all the browsers that are out there. For WebGL, it's pretty easy. I mean, you've got Safari, you have Firefox, you have Chrome, you have Opera. Internet Explorer, I'm never quite sure if it's in the game or out of the game.
Well, there's two levels that you can get. With the Internet Explorer, you can get some Google stuff to add, make it run, and Microsoft says varying things about whether it's going to be supported in the future. But you want me to add on to your answer? Yeah, yeah. You know, sort of, I'd add on some practice. I just love doing stuff in WebGL now, but it is a big transition for a lot of people to start working in JavaScript. It's not that there are lots of gotchas in there, and there's a sort of a among my. I'm an ex-academic. Academics don't love it, and so it's very hard to get into the curriculum for you people who are educators. But the other really practical problem, two practical problems, is one is that when you start working on the web, you have all kinds of security issues which didn't arise when you were just working, you know, doing workstation or desktop OpenGL. Those things didn't arise and they weren't considered. And when I talk to people on the standards committee, you know, they're worrying about those issues now, which people who do web development are all aware of. So that's a problem. The other problem is when you add another level of of having the web plus OpenGL. Debugging can be quite an adventure. Plus, I want to emphasize what Dave said, that I've done some performance tests across different browsers on different operating systems, and the performance varies all over the place, and whether it's the OpenGL that's causing the problem, whether it's the JavaScript engine or what is really contributing to the performance, is really hard to get it. But that's all going to evolve in the next couple of years, so you know, don't worry too much about what's happening now.
I agree wholeheartedly, except you're still an academic.
At heart.
At heart. Anyone?
Another question, just for, how do you guys decide what goes into OpenGL ES, and do you ever see there being a convergence with like the normal OpenGL APIs? Is that driven by mobile hardware, or how does that work?
Excellent question. So the question, do you mind if I take this one, since it's my day job? The question is, yeah, how do we determine what goes into OpenGL ES? Fortunately, not directly my day job. There's another working group called the OpenGL ES working group, led by a fine gentleman named Tom Olson. There's a whole bunch of Kronos-related BOFs that talk about all the APIs this coming Wednesday evening, I think, put on by the Kronos group. Stop in, hear the latest. But to directly answer your question, that organization actually has a lot more people in it than the OpenGL ARB, because there's that many more hardware vendors. I mean, that's kind of where a lot of the active development for the masses is happening. They contrast how OpenGL ES evolves by looking at what kind of hardware capabilities are there, what are the requirements in the space, because in an embedded environment, like when you have a phone, right, it's battery powered, it has limited bus bandwidth, it doesn't have the same wide operating space that a desktop machine has. Desktop, right, you can have a 1,000-watt power supply in there, a huge GPU, a massive fan, tons of bus and those kind of things. We can't do that in mobile devices. And then when I say we, mobile is what I'm working in nowadays, right? Because you burn your leg off or burn somebody, and we don't want that. Or the experience lasts for 3 minutes and then your game is done, and so is your phone. So we have to really weigh, you know, what is battery technology at that time, what's capable of being actually put into chips, what does the supporting structure of the bus speed, the CPU, how much memory is available. And the OpenGL ES group, they're experts in there who've built systems for a very long time, look at that kind of going, yeah, okay, we're kind of good. We haven't found a great big need for, say, geometry shaders down in mobile yet, but maybe that'll get there. Which leads into the second part of your question about the convergence of the APIs. The way it's working now, OpenGL ES is rapidly heading in that direction. And I suspect you'll see some kind of convergence, because at some level, right, people have to write an OpenGL app to run on the desktop and the OpenGL ES app to run on a mobile phone. Once again, that's not a complete truth, because OpenGL ES is supported on desktops as well. But, you know, this is work for the driver writers. They have to test two paths and do conformance on both APIs. So having that combined together is a really good thing. It's also the fusion of embedded with desktop. You know, there's a converging marketing that's happened. So if you're asking me, you know, off the record, my personal opinion, yeah, there'll be a convergence of features. You know, when geometry shading and tessellation really take off in games, and those games migrate down to mobile, you see those features there in a heartbeat. But most mobile devices now are very, very capable graphics machines. They do all the texture mapping. They do all the vertex shading, completely programmable, full precision support. They're really quite amazing machines. So, yeah, just a matter of time.
Everything, you know, we showed here, which wasn't that much, but everything we showed here runs on my cell phone. I mean, which is an incredible thing to me, to just, you can whip out your phone and all of these 3D graphic stuff works on it now. It's,
So we'll switch. No, so, yeah, we're here for more questions, but this evening is the Papers Fast Forward. It runs from 6 to 8. If you've never been there, have a look. It's one of the funnest, most exciting parts of the show. The other part, I'm going to put a little plug in here. So there's another little conference happening in Vancouver next year. It's called SIGGRAPH 2014, and I'm the conference chair for it. So I'd really like if you guys, would come. That'd be cool. We thank you for hanging out this late in the evening. And coming to SIGGRAPH 2013, but if there are things you want to see at the show or whatever, drop by, drop me an email. But definitely, SIGGRAPH is everyone's community, so help make it what you want, and hopefully I'll see you in Vancouver. Aside from that, thank you very much for coming. I think Ed and I had a great time, as always, and appreciate all your questions. So have a great show. See ya.